Welcome back to the Snoozy Scientist, a calm corner of the universe where curiosity and science drift together to put you to a calm sleep. Tonight, we travel to the far north, to a world where a ceiling of ice has sealed away one of Earth's last frontiers for more than 10,000 years. The Arctic, a place so harsh that even sunlight struggles to reach the water below. Scientists know more about the surface of Mars than the deep subsurface of the Arctic Ocean. Beneath that frozen roof lies a realm darker than night, older than human history, and more hostile than almost anywhere on Earth. In this extreme cold, where steel becomes brittle and equipment fails without warning, life survives, entire ecosystems moving through the darkness, hidden beneath the frozen roof. Creatures adapted to a world without sunlight, warmth, or stable ground. Scientists have also recorded sounds they can't fully explain, deep, low frequency pulses carried through the water for miles. And when satellites scan the seafloor, they sometimes reveal ridges and shapes that shift or disappear between passes, as if the deep landscape were moving. There are still places beneath the Arctic ice where no human expedition has ever reached, not because we lack interest, but because the environment simply refuses to let us in. But why does the ice resist us? What unfolds beneath a barrier that swallows machines and fractures metal? How does an environment so cold and crushing still cradle life? And what secrets from Earth's ancient oceans are still locked below? Tonight, we drift into the Arctic's hidden world, a realm where pressure rises faster than instruments can measure, where darkness is deeper than water, and where the rules of exploration seem to change with every step. But before we begin, if you enjoy these calm journeys through Earth's mysteries, I would love it if you gently tapped like or subscribed. And if you feel up to it, tell me in the comments where you're watching from tonight and what time it is for you. Now, take a slow breath, let your shoulders soften, and together let us step quietly into the frozen ceiling that refuses to let us in. Above the silent water rests a ceiling of ice. It looks solid from a distance, a pale sheet stretching from horizon to horizon. But the truth is far more intricate than a single frozen layer. Sea ice begins as something simple. When the cold arrives and the water temperature slips below freezing, tiny crystals appear on the surface like frost on a window pane. They drift, collide, and gather into delicate slush. Then they tighten together and begin to thicken. Winter after winter, this process repeats until the ocean earns its roof. Arctic sea ice has a personality that is unlike the ice that forms in the Antarctic. The reason is not only temperature, but geography. Antarctica is a continent wrapped in ice, a massive island covered by glaciers that spill outward into the sea. The ice begins on land and moves toward the coastline before breaking into the water. The Arctic is reversed. There is no large landmass holding everything steady. The Arctic Ocean is surrounded by continents instead of being anchored by one. This creates a floating world. It is the ocean itself that freezes. The ice has no firm foundation beneath it, so it shifts, drifts, and reforms in constant motion. Scientists often divide this frozen roof into two forms. First-year ice is young. It has survived only a single winter. It is usually thinner, sometimes only a few feet thick. You can think of it like newly grown skin across the surface of the sea. Its crystals have not yet become compacted by years of cold. It is more easily broken by storms and currents. Multi-year ice has endured through many seasons. Winters have stacked upon one another. Salt has drained from its structure, squeezed slowly downward until the ice becomes harder and more resilient. It grows thick. Not just a few feet thick, but many. Some pieces can stand taller than a person, even when only the top is visible. The older the ice becomes, the more it takes on the strength of stone. It is pale blue within, dense and glassy, a record of time preserved layer by layer. Yet even this is not the whole story. The roof of the Arctic is alive in a slow and powerful way. It contracts with cold and expands with pressure. Winds push the ice sheets against one another, grinding them into jagged collisions. When two large pieces meet, they do not remain flat and gentle. They buckle and rise. Imagine tectonic plates on a miniature scale. The frozen slabs tilt upward, fold, and stack. Over days or weeks, they can form pressure ridges. These are not mere cracks, they are walls of ice that can grow taller than houses. In the muted twilight of the polar winter, they rise like frozen mountain ranges. Each ridge is a monument to the unseen forces at work beneath the surface. The water flows, the wind shifts, the temperature falls, and the ice responds. As the seasons pass, the frozen roof is never still. Even when the surface looks quiet, it is moving. The entire ice cap drifts in a slow circular dance across the top of the world. Currents beneath the surface pull at it. Storms push at it from above. The shifting plates break apart, then seal together again in new forms. Openings appear, only to freeze shut as the temperature falls. Channels form along pressure lines. When the light returns after the long winter, narrow lanes of blue water may appear where ice once stood. This transformation is constant. The Arctic roof is endlessly rewriting itself. There is a reason explorers describe the region as if it were alive. You can feel the motion even when your eyes insist on stillness. The creaking of distant ice, the deep rumble of ridges forcing upward, the faint crackle of crystals expanding in the cold. Every sound is a reminder that this ceiling has its own nature. It does not remain the same from one day to the next. It grows new forms out of itself. The hardness of multi-year ice means a ship can strike it and feel as if it collided with stone. First-year ice can break, shift aside, or refreeze into new patterns. Between these two forms lies a mosaic across the surface of the Arctic Ocean, a patchwork of young and old, fragile and strong, thick and thin, all held together by temperature, salt, and time. Some of this ice has been drifting for decades. It has seen storms rise and fall. It has traveled past distant coasts, collecting scars from collisions. Other pieces are newborn, smooth and white, waiting to be folded into the greater whole. Together they form a frozen landscape that is always in motion, a ceiling that cannot be measured by a single thickness or shape. This is why the Arctic roof is more than just frozen water. It is a dynamic layer between worlds. Above is the air of the polar north, cold and dry, shaped by winds that sweep across continents. Below is the dark ocean, with its hidden currents and ancient waters. The ice is the bridge between them, the boundary where the sea reaches toward the sky. So the Arctic's roof is not a static shelter. It is a restless skin that grows and shrinks, fractures and heals, rises and sinks. Every season reshapes it. Every storm and current writes new patterns into its surface. Even in its quietest moments, the ice listens to the forces around it, answering with movements too slow to see but too powerful to ignore. In this frozen ceiling lies the foundation of everything that happens below. There are places on our planet where the sun does not keep a steady rhythm. Its light does not rise and fall each morning and night like a dependable heartbeat. In the far north, the year is divided by a different clock. For nearly 6 months, the world above the Arctic Ocean sinks into uninterrupted darkness. The sun disappears beyond the horizon and leaves the frozen sea beneath a blanket of night. This is not the familiar darkness that comes at the end of a day. It is a deeper kind of absence. The sky becomes a veil of ink, unbroken for weeks at a time. The stars glitter with sharp clarity, and the moon glows when it appears, yet the sea below feels untouched by those faint glimmers. Darkness settles into every surface. It sinks into the ice. It drifts into the water. It fills the long, quiet hours. Time stretches in slow arcs, measured not by rising sunlight, but by cold and silence. Beneath this frozen roof, light fades even more quickly. Water eats it away. A few feet below the surface, the brightness begins to weaken. A few more, and it crumbles into shadow. Deep under the ice, sunlight does not simply dim, it vanishes. Even in the brightest months of the year, when daylight returns to the Arctic sky, the colors that reach the ocean are pale and scattered. So when winter arrives and darkness rules, the world below the ice becomes a realm without horizons. Vision collapses into blackness, shapes dissolve, distance becomes impossible to measure. For explorers and scientists, this eternal night is not an obstacle that can be solved with a brighter lamp. Light behaves differently when it travels through the sea. It bends and scatters. Water absorbs it and steals its warmth and color. Even powerful beams from robotic vehicles cannot penetrate far. The water swallows them within moments. What begins as a clear cone of illumination quickly becomes a faint glow suspended in a wall of black. Instruments feel the darkness too. Cameras and sensors struggle to hold a steady picture when there is nothing to reflect. They reach outward and find only silence. A submersible may descend beneath the ice with all its systems ready to listen and watch, but the darkness seems to resist every attempt to reveal what lies ahead. Metal and glass lose their certainty. Measurements wander. Readings drift. To understand why, you have to imagine how light and water speak to one another. Water is not empty space. It is full of tiny particles, drifting ice crystals, microscopic organisms, fragments of dissolved salt. Each one catches the light. Each one scatters it. What remains of a beam after a short distance is not a clear path forward, but a cloud of reflected fragments. Shadows appear where nothing moves. Objects seem closer or farther away than they truly are. Vision becomes a guessing game with no sure answer. Then there is the ice overhead. The frozen roof that shapes this environment does more than close the surface to sunlight. Its thickness and structure block what little radiance might filter through. Multi-year ice, compact and dense, is nearly opaque. Even first-year ice, thinner and more fragile, allows only a small fraction of light to pass. The sea below remains in near total night. Any glow that manages to slip through is spread thin and scattered in all directions. It becomes soft and formless, like a memory of illumination rather than the thing itself. Explorers describe the experience as stepping into a world without boundaries. The horizon disappears. The seafloor is hidden from view. A person or machine can move only by reading faint changes in temperature or pressure, or by trusting delicate instruments to guide the way. Yet even those tools feel the weight of the darkness. Batteries drain more quickly in the cold. Lights flicker. Cameras lose focus. Data becomes hazy or incomplete. For the creatures that live here, this world is not a hardship. It is home. They have evolved eyes that draw in every possible glimmer, or bodies that rely on senses beyond sight. Some fish create their own faint lights. Some use pressure or touch to navigate. They do not depend on the sun to see or survive. For them, the darkness is simply the way life exists. But for those who study this hidden realm, the absence of sunlight changes everything. It turns simple tasks into careful calculations. It makes the unknown feel even wider. The human eye is not designed for such deep blackness. We are drawn to light and shape and color. In this place, those familiar guides are gone. The only way forward is to listen to the water and trust the quiet tools that flicker in the dark. There are moments under the ice when the world seems to pause. The water stills. The echoes quiet. The light from a submersible fades into the surrounding black. For a brief time, the entire ocean feels suspended in night. It seems as if the darkness has no end and no beginning, only a vast quiet, a silence wrapped in cold. Here, beneath the frozen surface, light is a rare visitor, and the darkness holds the story of everything that remains unseen. Beneath the frozen roof of the Arctic lies a world shaped by weight, not just the weight of water, but the slow and steady force that builds mile by mile as you travel downward. Pressure is an invisible companion in every deep ocean. It presses against every surface, fills every gap, and occupies every space that is not already filled by something else. The deeper you descend, the stronger it becomes. That force is patient. It does not rush. It does not roar. It simply exists, quiet and constant, growing with every foot of depth. In the open ocean, this pressure is already intense. At a depth of 1,000 meters, the water pushes with a strength equal to many cars stacked on every square inch of surface. Under the Arctic ice, the environment is even more complex. The sea is sealed from above, held beneath a hard ceiling that shapes currents and creates condensed pockets of pressure. The ice does not relieve the weight. It adds to the environment that traps the water in place. The ocean has no room to rise or stretch upward. Its energy stays below, and every movement of water transfers that pressure outward and inward. It is difficult to imagine such forces on a human scale. On the surface, a simple plastic bottle feels firm in your hand. Drop that same bottle into deeper waters and it will collapse inward. Metal bends. Steel begins to groan. Even advanced alloys must respect the rules set by physics. Pressure does not negotiate. It follows a simple truth. For every meter of water above a point, the force increases. The deeper you go, the more the weight of the world rests on whatever descends. Engineers design submersibles to withstand these conditions, but even the best designs have limits. History holds several stories of machines that dared to go deep and never returned. One of the earliest deep-sea probes in the Arctic was lost within minutes of leaving the surface. It was equipped with cameras, reinforced hulls, and carefully sealed joints. Yet when it reached the darker water, the pressure found a weak point near an access bolt. A tiny flaw, hardly noticeable in a workshop, became the opening for a catastrophic failure. The water did not leak in slowly, it punched through. The probe was crushed from the outside in a single moment. Decades later, a research team sent another unmanned sub into the waters beneath the ice. It was stronger and heavier than earlier attempts, built with updated materials and tested for durability. It carried scientific instruments meant to measure temperature, currents, and salinity. It also carried the hope that technology might finally reveal more of the Arctic floor. Yet the same quiet force was waiting. The sub descended into a pressure zone formed between ice and deep water. The hull began to strain. Sensors showed stress levels rising. The final transmission was a burst of static. When divers later examined fragments of the vehicle, they found the metal plates folded inward like paper. Pressure acts differently underwater than on land. It presses equally in all directions. Every surface is tested. Every seam must be perfect. Machines built for the deep are shaped like eggs or spheres for a reason. Curves distribute force more evenly. Even then, the smallest imperfection can become the point where everything ends. A tiny crack that seems harmless on the surface widens at depth. A welded joint that looks smooth hides a microscopic flaw. Water finds these weak places and pushes until the metal yields. There is a well-known principle among deep-sea engineers. If the ocean can find a way in, it will. For every expedition that returns with data and images, there are others that face the silent strength of the sea. The pressure does not have to be violent to be powerful. It works through persistence. It waits for a change in temperature or a sudden shift in current. It watches for movements of ice above that alter the balance of water below. When those moments come, the force multiplies without warning. Some submersibles have survived astonishing depths. They are built with thick hulls and layers of protective material. They descend slowly and cautiously. Even then, they must accept that their safety is never absolute. At several thousand meters, a single square meter of hull withstands pressure equal to the weight of enormous buildings. No material is invincible. Engineers can only plan and hope that every piece holds. The reason failures are so sudden underwater is that water does not compress easily. When a submersible begins to collapse, the sea does not trickle inside. It rushes inward at incredible speed, filling every space in an instant. The force is so strong that air inside the vessel heats up. Metal bends, lights flash and go dark. A fragile world designed for life on the surface meets the ancient physics of the deep. Even modern systems that are tested again and again can fall short. Sensors malfunction when pressure grows too high. Electronic equipment warps, seals loosen. A vehicle that works perfectly in shallow water can become unreliable as it descends. The Arctic adds even more complexity. Temperature changes make materials brittle. Ice above shifts the pressure zones. The ocean below is uneven, full of unseen ridges and valleys. No two descents are ever the same. What makes these failures so compelling is not only the force of nature, but the reminder that pressure at depth is a quiet architect. It shapes the ocean floor. It guides the movement of water. It challenges every machine that enters its domain. Tiny flaws become gateways for collapse. A single bolt can decide the fate of an entire expedition. The deeper the ocean becomes, the more every weakness is revealed. This is the hidden strength of the Arctic's deep water. Pressure is not simply a barrier. It is a presence that waits in silence, testing everything that reaches into the cold. At first glance, the surface of the Arctic seems frozen in a moment that never changes. From above, the sea ice stretches out as a smooth sheet of white. It appears quiet and unmoving, as if time has settled into the landscape and decided not to pass. Yet beneath that calm appearance is a slow but relentless motion. The ice is never still. It drifts across the ocean as if guided by unseen hands. Ice drift is the journey that the frozen surface takes as currents, winds, and pressure push it across the Arctic basin. Even on the calmest day, when the air hangs motionless and the horizon appears steady, the ice continues to move. It can travel distances that are difficult to imagine. In a single day, the ice may drift several miles from where it began. Sometimes that movement is gentle and wide. Other times it is swift and unpredictable. It follows the flow of water beneath and the breath of the atmosphere above. It responds to changes in temperature and shifts in the polar wind. The motion is slow enough that the human eye cannot easily detect it, yet persistent enough that nothing beneath can escape its influence. Scientists who have placed tracking devices on the ice watch these paths unfold across maps like meandering rivers. The lines curve, twist, and even circle back. Some pieces of ice make long journeys, wandering for years across the surface of the Arctic Ocean, then ending their lives in warmer waters where they melt and disappear. Others gather together in tight packs. They crash into one another and fuse into clusters. The surface becomes an ever-changing mosaic. It is the very opposite of stillness. For those who explore beneath the frozen roof, this drift creates challenges that are both subtle and powerful. A submarine can enter the ocean through an opening in the ice, a gap created by wind or temperature, or even by human hands. That opening may seem wide and stable, yet as the ice shifts, it closes without warning. A sub that descends into the water may return to find the entrance sealed behind it. The once open path has become a trap. Ice plates can slide together like the closing of a giant door. A span of water that was safe moments ago becomes a prison with no clear escape. There are stories of submarines that surfaced with their crews, expecting to rise through a familiar opening, only to find solid ice overhead. In those moments, the ocean becomes a labyrinth. The sub must travel beneath the surface, searching for a new route to safety while the ice above continues its slow wander. The pressure from the moving ice can crush a vessel. It can press against the hull and force it downward. It does not need speed to be dangerous. It only needs time. When a submarine is caught between slabs of ice, the danger increases. The structure overhead can shift, even break apart, and then fall together again. The cold creates jagged edges and heavy sheets. The submarine becomes vulnerable in the tightening grip of a moving landscape. Explorers know that the ice does not need intention to be powerful. It only needs movement. What makes the surface so deceptive is its quiet nature. The illusion of stillness invites the mind to believe that the ice is anchored in place, yet every piece is in motion. The ice follows the flow of great rotating currents that circle the Arctic basin. These currents are driven by wind patterns and differences in temperature. They guide the ice across thousands of miles in slow arcs. You can stand on the surface and feel as if the world is steady beneath your feet. In reality, you are riding a frozen platform that is gliding over the ocean. Even small shifts can be enough to trap a submarine or block the path of a research vessel. Ice that looks smooth can hide fractures below where entire sections are creeping past one another. A gap in the surface can vanish beneath a blanket of snow. The edges of ice plates can move silently, joined by nothing more than the whisper of water and cold. These movements create sudden cracks, towering ridges, and long pressure lines. A machine that ventures too near may be pushed against these shifting borders. A single change in the wind can close the ocean's surface in one area while opening it in another. The drifting ice also affects how explorers navigate. Instruments that guide submarines must take the movement into account. A map that was accurate in the morning can be incorrect hours later. The ice has changed position. New obstacles now lie ahead. Openings that were safe have shifted miles away. Underwater, the landscape is never the same twice. This constant motion is what gives Arctic sea ice its character. It is a living surface shaped by forces that never rest. The frozen ocean is an expression of wind, water, and cold. To look upon it and see stillness is to miss the truth. Beneath the calm surface and the pale expanse, the ice is always moving. It slides across the sea like a slow tide of frozen earth. This motion is gentle to the eye and powerful to the world beneath. It holds the ability to trap the machines built by human hands, to reshape openings in moments, and to turn familiar passages into walls of ice. The drifting surface is a quiet reminder that even in the most frozen places on Earth, nothing is truly still. Across the frozen surface of the Arctic, there are places where the ice breaks apart. These cracks and passageways are called leads. They form when shifting plates pull away from one another, leaving long stretches of dark water exposed to the open air. From above, they appear as thin lines carved into the endless white. From below, they are pathways to the surface, narrow windows where a submarine can rise to breathe and take its bearings. These openings are lifelines for anything that travels through the deep water. They offer the only way for air to reach the ocean and for machines to return to the world above. Yet, they are also temporary. Even the largest of them is never secure. They widen and contract as the ice drifts. They twist and change shape without warning. They disappear as quickly as they appear. The cold works like a sculptor. When a lead opens, the freezing air begins to shape it almost immediately. Thin sheets of ice form at the edges. They stretch toward the center. The ocean responds with its own rhythm. Waves roll beneath the surface. Wind pushes the plates together again. Before long, the opening begins to close. A ribbon of open water becomes a patch of thin ice. A patch becomes a solid sheet. Sometimes this transformation takes hours. Other times it takes minutes. There are records of leads that lasted for only a brief moment, long enough for a ship to notice them but not long enough to cross. Some open in one direction while others close somewhere else. The surface becomes a shifting puzzle made of pieces that never stay still. For submarines navigating the world below, these changes are more than an inconvenience. They are the difference between safety and danger. When a submarine travels beneath the Arctic, it does not surface through a single fixed path. It relies on the knowledge that an opening exists. Instruments track where leads have been. Maps show where the ice appeared thin. The vessel follows these signs and trusts that one of the paths above remains open. Yet the ice is always moving. A lead that seemed wide when the submarine descended can seal shut during the journey. The change is not loud. It does not announce itself. Ice plates slide together in silence. Crystals form along edges. Pressure pushes pieces into place. What was once open water becomes a roof of ice that stretches unbroken in every direction. There have been moments when submarines have risen toward the surface, expecting to see water and instead found solid ice overhead. The first contact is gentle. The submarine touches the surface and senses resistance. The crew listens. They wait, but the ice holds firm. The escape route is gone. Imagine the scene. An underwater vessel surrounded by darkness, rising carefully, trusting the opening above it, only to meet a barrier that was not there before. The submarine cannot simply break through the ice. The roof overhead may be several feet thick. It may be reinforced by layers of pressure. Even a thin layer can become strong when supported by cold and time. Some submarines have been trapped in these conditions. They have been forced to move through the hidden world below, searching for another lead while the ice continues its slow dance. The ocean becomes a maze. Every turn is uncertain. Every calculation must consider the shifting surface above. The submarine must stay in motion. Waiting is not an option. The ice will not turn back. What makes these openings so unpredictable is the combination of forces that shape them. The wind blows across the surface, pulling and pushing the plates. The current below tugs in another direction. Temperature shifts, freeze the water more quickly, or make the ice brittle. Pressure from moving ridges creates new cracks while sealing old ones. No single factor controls the transformation. They all work together, creating a landscape that changes moment by moment. Leads that appear wide and safe are sometimes nothing more than temporary breaths in the frozen world. The ocean exhales, the ice parts, then the sea breathes in again and the opening closes. For the creatures who live there, this rhythm is familiar. Seals move between holes and cracks, knowing instinctively which passages are safe. They listen to the ice and wait for the right moment. Humans do not have those instincts. Machines do not either. Instruments can measure, maps can guide, yet nothing can predict exactly how the ice will behave. This is why the openings are both a gift and a risk. They offer a way through the frozen ceiling. They are the only places where water meets sky, but they can vanish without a sound. A submarine may rise to the surface and find itself beneath a world that has changed in the hours it spent below. In the Arctic, the surface is not a stable shield, it is a shifting gateway. The leads and openings are reminders of how fragile access can be. They are fleeting paths that come and go with the quiet movement of wind and water. What seems safe one moment can disappear the next. Here, under the frozen roof, escape routes are never promised. They are written in ice, changed by time, and erased by the quiet touch of cold. If you could peel away the ice and look into the ocean beneath, you would see movement so vast and deliberate that it resembles a slow heartbeat. The Arctic is not a still bowl of water sealed beneath a frozen ceiling. It is a place where currents weave through the darkness in winding and powerful paths. They travel through the deep basins and channel through narrow passages between underwater ridges. They rise and fall like tides that never rest. These currents form a hidden network. Scientists sometimes call it an underwater conveyor, but that word does not capture the complexity of the motion. The water is not pulled by a single force. It is guided by temperature, salinity, pressure, and the subtle connections between distant oceans. Warm water from the Atlantic enters through deep gateways and sinks beneath the surface. Cold water formed along the ice edges sinks even farther. As they travel, the two flows mix and separate again, layering through the deep sea. It is easy to imagine the Arctic Ocean as sealed and isolated, but it is one of the most connected bodies of water in the world. Through narrow channels and deep straits, it exchanges water with the Pacific and the Atlantic. The ocean beneath the ice moves like a living system. It is part of a loop that stretches across the globe. Water that begins in one distant place may spend years or decades traveling the Arctic's depths before rising again into another ocean. In the darkness below, these currents reveal their strength. They are not surface winds that can be read by watching waves or clouds. They move in silence. They can be gentle for long stretches before accelerating into swift flows. A submersible that enters one of these channels can be caught in the motion instantly. There are stories of probes that drifted far from their intended paths. Instruments detected them being pulled sideward, dragged into deeper water, or diverted into narrow passages where the currents squeeze through underwater valleys. The forces that guide these undercurrents are unique. In many oceans, warm water floats near the surface and colder water sinks. The Arctic reverses this pattern in strange and beautiful ways. Warm water can slide beneath colder layers because its salt content is higher. Cold water that forms near the ice becomes heavier still, dropping into great depths. These layers of water glide past one another in slow, quiet rivers. If you could touch one of these boundaries, it would feel like a thin wall. The water above may be cold, and the water below even colder, yet the boundary holds each layer apart. Submarines that move through these layers must navigate with caution. The currents can seize a vessel and shift its direction. A machine that is carefully tracing a path along the seafloor can suddenly be pulled away. Some vehicles have lost contact in these currents. They were carried to places where retrieval became impossible. The ocean carried them like leaves on a river, turning them around ridges and pushing them into new channels where the path was no longer familiar. Unlike other oceans, the Arctic currents do not follow a predictable pattern. They bend and twist around underwater mountains. They respond to changes in the ice above. When the ice moves, the water beneath moves as well. During winter, when the surface is locked under darkness for months, the currents shift to carry colder, saltier water deeper. When summer brings melting, fresh water expands across the surface, altering the flow. No two seasons are ever the same. The ocean is always writing and rewriting its pathways. Some currents are so powerful they can sweep equipment away. They carve through the seafloor, moving sediments and reshaping underwater landscapes. The deep currents rise in plumes of ancient water that has not seen the surface in centuries. In these places, the ocean seems to breathe. It exhales water from the depths and inhales new water from distant seas. What makes these currents unique is not just their strength, it is the strange combination of forces that shape them. Temperature, salt, and the frozen surface join together. The ice acts like a blanket, trapping heat and sealing cold. The seawater becomes layered like a story told through time. Each layer carries a memory of where it has been. It might have traveled from the warm Atlantic. It might have risen from shadowed trenches. It might be water that froze in another age and melted again. No other ocean behaves quite like this. In the Arctic, the currents do not simply flow. They form networks that branch and converge. They move in spirals and loops. They brush the ice above and stir the sediments below. The ocean is always in motion, guided by patterns that stretch across continents and through time. For explorers and scientists, these hidden rivers are beautiful and unpredictable. They carry messages from the distant past and shape the future of the sea. Moving through them is like stepping into a world where gravity and pressure are rewritten. The currents are reminders that even beneath the quiet surface, the Arctic holds a vast and restless power. Far below the drifting ice and the restless currents lies another world. It is a landscape as wide as continents, yet almost entirely hidden from our eyes. The deep sea floor of the Arctic is one of the most mysterious places on Earth. Only a small portion has ever been mapped in the detail that scientists rely on to understand terrain. Less than 10% of the region is known with any useful clarity. The rest is a blank page, a canvas of possibilities that stretches across the bottom of the world. In other oceans, maps have been drawn over many decades. Submarines have traveled through them. Sonar has traced the shape of mountains and trenches. But beneath the Arctic ice, mapping is a struggle. You cannot simply point your equipment downward and expect clear echoes. The ice above scatters sound. It bends and redirects signals. The water itself absorbs the pulses sent from ships and submersibles. What returns is often blurred, faint, or incomplete. Even when explorers try to chart the seafloor, the images they receive are often distorted. The ice makes it difficult to know whether a shadow in the echo is a ridge or merely noise from the surface. Sometimes features appear to move when only the ice has shifted. Sometimes entire mountains hide in plain sight, disguised by the effects of cold and distance. Yet the deep geography of the Arctic is not empty. Over time, scientists have uncovered astonishing structures beneath the ocean. There are vast underwater ridges that stretch for hundreds of miles. Some rise like silent mountain chains across the floor of the basin. They divide the Arctic Ocean into isolated basins and deep trenches. They guide the currents and shape the flow of ancient water. One of the most surprising discoveries is that some of these ridges were found only in recent decades. The Lomonosov Ridge was once thought to be a lost continent, a fragment of land that broke apart long ago and now rests beneath the sea. Explorers first detected it by accident. Their instruments showed an unexpected rise in the seafloor. something far taller than expected in the deep Arctic. Later missions confirmed that this ridge stretches between Greenland and Siberia. Until then, no one even knew it existed. There are other features as well, hidden from the world until scientists looked deeper. Underwater plateaus rise like islands that never reach the surface. Trenches sink into darkness where light has never reached. These places are like untouched worlds, filled with sediments that hold the story of ancient Earth. Some were formed by volcanic activity long ago. Others were shaped by the slow movement of the ocean floor, fractured and pulled apart in silence. Mapping these places is challenging. Sonar, which is the main tool for charting the deep, must send sound waves downward and wait for them to return. The echoes draw a picture of the world below. But the ice disrupts the signals. It reflects them in different directions. It adds layers of noise and interference. The result is that sonar readings must be interpreted with caution. A scientist examining the data must determine what is real and what is an illusion caused by the surface. Ships also cannot easily travel in straight lines beneath the ice. They must navigate through narrow channels. They cannot always reach the areas they wish to study. The Arctic becomes a maze even at the surface. Some vessels carry advanced equipment that can see through ice, yet the image remains incomplete. The ocean floor is too far away, the paths beneath too complex, and so much remains unmapped. Some of the most detailed views of the Arctic seafloor have come from submersibles. These vehicles travel beneath the ice and get closer to the bottom. They have revealed cliffs that rise from the deep. They have filmed rocky slopes where no one expected to find solid ground. They have shown fissures and canyons carved by ancient forces. Yet these missions are rare. They are difficult to plan. The ice moves, the currents shift, and a single journey only captures a single line of exploration. Even with modern technology, the Arctic remains a frontier. There are areas beneath the ice that no ship has ever passed over. No sonar signal has ever mapped. No camera has ever captured. The darkness guards these places. The cold preserves them. They wait beneath the frozen ceiling like hidden valleys in a distant land. The seafloor may hold answers to questions about Earth's past. Sediments there carry records of climate changes that happened long before humans arrived. Fossils may rest in those layers. Volcanic vents may shape the chemistry of the ocean, but for now, most of it remains unseen. Scientists look at the tiny slivers of knowledge they have gathered and imagine the vastness still undiscovered. When explorers speak of the Arctic deep, they do not talk about what they have mapped, they talk about what they have not. The unknown stretches farther than the known. The unmapped areas are places where the ocean floor has never been traced. They are the silent majority of the Arctic basin. The deep sea here is not defined by smooth plains. It is sculpted by mountains and ridges and shadows. It is a place where the Earth's story continues in quiet mystery, hidden beneath the ice and waiting in the dark. There are stories scattered across the history of Arctic exploration, stories not of people or animals, but of machines. They were built to listen, measure, and observe. They were sent into the darkness beneath the ice with the hope that sensors and steel might succeed where human senses cannot. Some returned bearing fragments of knowledge, others vanished without a trace. In this silent world, a lost machine leaves no trail. The ocean does not ripple to reveal its path. The ice above seals any sign of passage. The darkness swallows every footprint. When a probe disappears, all that remains is the memory of its final transmission and the lingering question of where it finally came to rest. Many of these machines were unmanned submersibles, Designed with careful precision, they carried cameras, sonar arrays, and instruments to measure the subtle qualities of the Arctic water. Before they left the surface, their paths were planned and their sensors calibrated. Then they descended into the deep, leaving behind the world of sky and wind. Some of these vehicles returned with valuable measurements. They captured images of rock formations and recorded the patterns of the deep ocean currents, but not all of them were destined to come home. Beneath the ice lies a world where mistakes are permanent and recovery is almost impossible. There is no open access to the surface. There are no support ships that can quickly retrieve a failing probe. Once a machine goes too deep or drifts too far off course, it crosses into a realm where human help cannot follow. The reasons for these losses are rarely dramatic. There are no explosions or dramatic collisions. Instead, the failures are quiet and sudden. A small tear in a sealing ring allows water to seep into delicate electronics. A battery drains faster than expected in the cold. A current seizes the probe and drags it off its planned path. A pressure zone squeezes a frame and warps a cable. The Arctic does not need violence to claim a machine. It only needs the patience of time and the weight of water. As a probe drifts deeper into this world, radio signals cannot reach it. Communication depends on sound waves, but these too must rise through hundreds of meters of moving water and shifting ice. A single sheet of ice can block a message. A thick slab can silence the strongest signal. Once contact is lost, the machine becomes an echo. It continues its descent into the silent world below. Recovery is nearly impossible for a simple reason. Even if a probe sends a distress signal, there is often no direct route to reach it. The ice overhead may stretch for miles. The surface may be sealed, ridged, or fractured. The path below may be too narrow for a submersible to follow. The currents may have changed direction. Even if the probe remains intact, there is no guarantee that anyone can reach the place where it finally stopped. The Arctic holds on to its secrets. Yet some of these lost machines spoke before they disappeared. Their final transmissions were sometimes brief, sometimes detailed. They whispered about currents stronger than expected. They measured temperature shifts that hinted at ancient water rising from the depths. They captured images of the seafloor that revealed unexpected shapes and towering ridges. In their last moments, they became recorders of places no human eye had ever seen. One submersible sent a final signal that detected strange patterns of sound. A low hum carried through the water, steady and deep. The frequencies were unlike anything recorded in other oceans. Scientists reviewed the data again and again. They did not know whether the sound came from shifting ice, moving water, or something hidden even deeper. The probe vanished before anyone could investigate further. Another machine recorded tiny particles suspended in the water. These were not sediments falling from the surface. They were fragments of minerals rising from the seafloor. The patterns suggested volcanic activity beneath the ice. The data hinted at vents releasing heat and minerals into the water. Before more could be learned, the machine stopped responding. Even when a probe disappears, it leaves behind a moment of understanding, a small piece of the puzzle, a hint of the world beneath. For every lost machine, there is a memory of its final message. It may be a photograph of a rocky ledge or a measurement of an ancient current. It may be the signal of a sudden pressure change or the faintest sound of something moving in the deep. The silence that follows is not empty. It is the silence of a story cut short. The Arctic holds these machines like relics in a frozen vault. Their steel frames rest somewhere beneath the shifting currents and the layered darkness. Their sensors are quiet now. Their lights are dark. Yet the data they sent before disappearing continues to guide scientists in their understanding of the deep. Here, beneath the frozen surface, the machines do not speak again, but in their silence, they remind us how little we know about the world below. Far beneath the drifting ice and the restless machine of currents lies something quiet and ancient. It is not a mountain or a ridge, it is not a hidden cavern or a lost ship. It is water. Not ordinary seawater, but a layer so old that it carries the memory of Earth long before humans ever appeared. Oceanographers call them ancient waters. They have traveled across oceans and through deep basins for longer than any river has flowed across land. They have changed slowly, passing through narrow channels and sinking where salt or temperature guided them downward. Some of these waters last touched the surface thousands of years ago. Others may be much older still. They do not simply drift, they wait. The Arctic is one of the few places on Earth where these ancient waters gather in silence. The shape of the ocean floor creates deep basins that act like hidden bowls. The continental shelves rise on every side, forming walls that prevent the oldest layers from spilling out. The water sinks into these depressions and becomes trapped. Over time, new layers form above it, pressing the ancient water deeper into the world below. Chemical signatures are the clues that reveal this story. When water circulates, it carries dissolved gases and minerals. These substances become markers. They change as the ocean interacts with the atmosphere, as currents stir the layers, as life uses oxygen or releases carbon. In places where water sinks to great depths, these markers remain locked away. They tell scientists where the water has been and how long it has been traveling. Researchers have captured samples from the Arctic deep and discovered unusual patterns in the chemical makeup. They found concentrations of nutrients and trace elements that did not match the waters above. Some of these signatures are so distinct that they point toward ancient origins. The age of these waters can be traced not through fossils or rock, but through the chemistry that has remained undisturbed through time. What makes the Arctic so special for the preservation of ancient water is its unique geometry. The ocean floor here is divided into deep basins, separated by ridges and plateaus. These underwater walls act like barriers. Unlike other oceans where deep water eventually rises and mixes with the surface, the Arctic's deepest layers remain contained. They do not circulate in the same rhythm that shapes the rest of the world's seas. They are sheltered beneath the ice and beneath the weight of the water above. Imagine these deep basins as time capsules. They hold water that has seen ages come and go. They hold the last traces of currents that once flowed in a very different Earth. The temperature of these layers remains steady and cold. The darkness is complete. No sunlight travels here. Life exists, but in a quiet and slow-moving way. Bacteria and small organisms drift through the depths, feeding on nutrients that have settled over centuries. Over this vast span of time, the ancient water preserves a part of our planet's memory. Its chemistry contains the signals of past climates. It shows how the oceans once moved and how they carried heat and energy across the globe. By comparing the composition of these waters with those in other oceans, scientists can trace the history of global circulation. They can learn how the Arctic helped shape the climate of the Earth, even in the distant past. Some of these waters may have been formed when vast ice sheets covered northern landscapes. Others may date to periods when the world was warmer. As climates shifted and oceans changed, the deep basins of the Arctic continued to hold on to their hidden layers. The oldest water cannot escape easily because the movement of the deep currents is slow and the basins are steep. The water remains in place, protected from the storms and waves that churn the surface above. Gathering data from these ancient layers is difficult. Probes must travel into the deepest trenches beneath the ice. They collect samples and record the chemical signals that reveal the age of the water. Even then, only a small part of the deep Arctic has been studied. The rest remains untouched. In those places, the water carries secrets that may be older than human civilizations, perhaps older than the first stories ever told. These ancient waters do more than hold memories. They influence the world above. They connect distant oceans. They carry salt and cold that shape the global climate. In some ways, they are part of Earth's oldest system of movement, a system that predates human knowledge and will continue long after. The water moves slowly and quietly, circling the basins and flowing across unseen boundaries. It does not rush. It does not roar. It holds a history written in temperature and salinity. It tells the story of an ocean that has never stopped changing and a planet that has been shaped by time. Deep within the Arctic, where darkness has settled for thousands of years, the oldest waters remain, patient and still. They are a library written in liquid form, holding knowledge older than humanity itself. Far below the shifting ice, where the cold grows deeper and the dark becomes complete, life still finds a way to exist. It does not take the familiar shapes we expect. There are no forests or fish in these depths. Instead, the ocean is home to some of the smallest and most resilient organisms on Earth. They are microbes, so tiny that entire worlds of them could rest on the tip of a single grain of sand. Yet in this hidden sea, they are the true pioneers. These microbes live in a world that never sees sunlight. The conditions above, where shifting ice and moving currents shape the cold ocean, are already difficult. But in the deepest trenches and hollows of the Arctic, the challenges multiply. There is no hint of daylight to guide growth. Temperatures stay close to freezing. Pressure presses against every surface. And yet these organisms survive. They do not only endure the darkness, they rely on it. In the absence of sunlight, life must follow different rules. These microbes do not use photosynthesis. They do not collect light to turn into energy. Instead, they draw their strength from the chemistry of the ocean. Some latch onto minerals rising from the seafloor, using chemical reactions to build the energy they need. Others feed on dissolved compounds that drift through the water. Their world is defined not by light but by chemistry. Scientists call them extremophiles because they thrive in conditions that would destroy most other forms of life. They have found ways to survive that seem almost impossible. Their cells are suited to the cold. Their membranes are soft and flexible instead of rigid. Their proteins are shaped in ways that allow them to continue working even when temperatures plunge. It is as if their bodies speak the language of winter. In some places, these microbes form entire communities. They gather on the surfaces of rocks or in the thin layers of water trapped between crystals of ice. They create thin films that glow faintly when viewed under special lights. Within those layers, they share nutrients and exchange chemical signals. These are not isolated organisms drifting alone. They are small societies built in the heart of the deep. Some extremophiles live even more extraordinary lives. They sleep for long periods, waiting for small amounts of energy to appear. When the ocean offers a spark, they awaken and begin their quiet work. Others move slowly through the water, drawn by faint gradients of chemicals that serve as their compass. They drift toward places where conditions are right, guided by nothing more than whispers of molecules. What makes these microbes so remarkable is not only where they live, but how they grow. They have survived in sub-zero temperatures for thousands of years. Some are found in pockets of water sealed within the ice itself, trapped since ancient times. Others cling to the seafloor, where minerals leak into the water from deep below. These places are like laboratories created by nature. They show us how life can adapt when every familiar resource is gone. When scientists study these organisms, they study more than survival. They study the possibility of life in places far beyond Earth. If microbes can thrive in darkness, beneath ice, and without sunlight, then perhaps life is not limited to warm and gentle conditions. Perhaps life can emerge anywhere there is energy and the right ingredients. Some researchers look at the Arctic and see a mirror of distant worlds. They think of the oceans beneath the ice of Europa, one of Jupiter's moons, or the frozen lakes on Mars. These places share the same qualities of cold, darkness, and hidden water. The extremophiles beneath our own ice may be showing us what life on those distant bodies could look like. These microbes remind us that life does not always need light or warmth. It does not require a friendly surface world. It only needs time, chemistry, and the patience to adapt. Each cell contains the instructions for survival in one of the harshest environments on Earth, and each one challenges our understanding of what is possible. If a single-celled organism can build a home where sunlight never reaches and temperatures remain close to freezing, then life may be far more common in the universe than we once believed. The Arctic deep becomes not just a hidden world on our own planet, but a model for life in places that have yet to be explored. In this quiet and ancient sea, where currents move slowly and darkness fills every space, these extremophiles continue their work. They draw energy from the earth itself. They build communities where no light can shine, and they leave us with a lesson written in chemistry and patience. Life can take root in places we once thought impossible. The ocean beneath the Arctic ice is not a simple flat ceiling of frozen water. It is shaped by movement, by pressure, and by slow sculpting forces that continue through every season. The same shifting ice that opens and closes leads also creates spaces beneath the surface. These are the subglacial caves and hollow chambers, hidden pockets carved into the underside of the ice sheet. They are spaces where the ocean and the frozen roof meet in delicate balance. When seawater moves along the bottom of the ice, it does not always freeze into a smooth sheet. Warm currents can create hollows, melting small pockets and shaping arches of ice overhead. Over time, these small openings become larger. The ice itself bends and warps around them. It grows into domes and tunnels, shaped like the vaulted ceilings of ancient cathedrals. These underwater caves do not form through solid stone or erupting volcanoes. They come from the meeting of temperature and motion, from the quiet breath of the ocean against the underside of the ice. Some of these caves are vast. They stretch for hundreds of meters beneath the frozen roof. Others are narrow passages, wide enough for only a small submersible to slip through. The walls of ice above are smooth in some places, jagged in others. Crystals form patterns that shimmer in the faint glow from a vehicle's light. If a person could drift through these spaces, it would feel like traveling beneath a world turned upside down. The ceiling becomes the landscape. The water is the sky. Inside these chambers, the temperature is strange. The cold should be constant and absolute, yet something different happens when seawater flows beneath the ice. The water carries heat from the deeper ocean. Not enough to melt the ice entirely, but enough to change the temperature by small amounts. Even a difference of a few degrees can shape the cave. It allows the ice to melt and refreeze, shifting the architecture of the space. These temperature anomalies do more than build the cave. They create an environment that is unlike the open ocean. In some chambers, the seawater becomes a layer of warmer fluid resting beneath the ice. In others, Fresh water from melting ice flows into the space. The layers settle into patterns that move slowly with the current. Warm water rises, cold water sinks. The strange chemistry of the Arctic shapes each chamber, giving it a signature that is unique. Some of these caves form along the ice edge, where the frozen surface meets the open water. Others are trapped deep within, far from any opening. Scientists using sonar and submersibles have discovered hollow spaces large enough to surprise even the most experienced explorers. They are shaped like hidden rooms within the frozen world. Sometimes they appear unexpectedly, their existence revealed only by the bends in a sonar echo. Other times they reveal themselves as mysterious gaps where light and sound behave differently. It is in these chambers that researchers hope to find unusual forms of life. Microbes and small organisms drift through the water inside them. They cling to the ice walls or swim through the layers where seawater meets meltwater. These caves hold their own ecosystems. The environment is dark and still, yet never truly frozen. Water circulates slowly. Nutrients settle into the hollows. Some chambers may hold conditions that have remained steady for years. Yet, despite their potential, most of these subglacial caves remain out of reach. The same ice that forms them also guards them. The entrances may be too small or too fragile for a submersible to enter. The tunnels may twist in sharp turns, making navigation dangerous. The ice overhead could shift at any moment. A chamber that exists today may close tomorrow. These spaces are shaped by forces that do not pause for human curiosity. Even when explorers find a cave, reaching it is difficult. Submersibles must approach from below, tracing narrow corridors between ice and water. The paths are unpredictable. Instruments struggle to map the shape of the chambers. Sonar signals bounce from jagged surfaces. The ceiling is always moving. A hollow that is safe in one moment becomes unstable when the temperature changes or the pressure of the water shifts. Some of the largest chambers may never be seen. They lie far beneath the surface, protected by thick ice and deep currents. The pressure makes travel dangerous. The narrow openings make maneuvering nearly impossible. The Arctic keeps these spaces hidden, allowing only brief glimpses through the windows that technology provides. Yet even a brief glimpse is enough to spark wonder. The idea of caves beneath the ice reminds us that the Arctic is not a single frozen block. It is a world of layers and hidden rooms. It is a place where water and ice share the same boundaries. The caves form slowly and fade slowly, shaped by the smallest changes in heat and motion. They are secret places where the ceiling of the world becomes something more. Spaces carved by nature in silence. Rooms that hold water older than memory and darkness that has never seen the sun. Most are unreachable, but they exist all the same, waiting in the quiet depths where the frozen roof meets the sea. Beneath the Arctic Ocean lies a type of cold that is unlike anything on the surface. It is ancient and heavy, and it does more than freeze water into ice. It freezes the seafloor itself. This frozen layer is known as subsea permafrost. It stretches across wide regions under the Arctic shelf, and within it, something extraordinary is trapped. Methane, one of the simplest and most powerful molecules on Earth, sleeps inside this frozen ground. Methane forms in many ways. It can be produced by ancient organic matter that decomposed long ago. It can come from chemical reactions deep within the Earth. In the Arctic, much of it became trapped when ice sheets expanded across the land and sea. Over thousands of years, these icy layers grew thicker and heavier. They sealed the methane inside pockets and cavities beneath the seafloor. The gas could not escape. It became part of a frozen archive of the planet's distant past. These deposits do not look like large reservoirs of gas. They are held in crystals known as methane hydrates. The hydrate looks like ordinary ice, but it is built from water molecules that form cages around the methane. It is a solid that contains a gas, stable only under very specific conditions. Cold temperatures and high pressure keep it locked in place. If these conditions change, the hydrate loses its stability. In the deep ocean, the pressure is strong enough to hold the hydrate together. The cold is steady enough to keep it frozen. But in certain places, the balance becomes fragile. When a submersible or probe disturbs the seafloor, the warmth of its lights or the vibrations of its instruments can make the ice crystals shift. A small change in temperature can cause the hydrate to release methane suddenly. The gas bubbles rise through the water in streams, sometimes so thick that the ocean itself seems to boil. This release is not always violent. Sometimes the gas emerges quietly, forming small pockets of bubbles that rise to the surface in slow columns. Yet the destabilization is significant. The hydrates are held in place by a delicate balance that can be interrupted by the slightest disturbance. Scientists who study these deposits have learned that even touching the seafloor with an instrument can alter its chemistry. Subsea permafrost is also shaped by the currents of the ocean. Warm water that drifts into these areas can melt the ice from below. As the permafrost softens, the methane escapes, the deeper layers become fragile. The seafloor sinks or collapses in certain places. Underwater craters form where the hydrate once held the ground in place. These shapes are visible on sonar as depressions and scars scattered across the Arctic shelf. The release of methane creates something else as well. It produces distinct sounds that travel through the water. The gas bubbles rise quickly and burst at the surface. As they escape, they produce acoustic signals that scientists can detect from far away. These sounds are sharp and rhythmic. They echo through the ocean in patterns that reveal the size and speed of the release. Hydrate releases have acoustic signatures that are unlike any other sounds in the deep. The bubbles vibrate as they rise. They create a frequency that can be measured and analyzed. In some places, the sounds become a chorus. Thousands of tiny bubbles sing through the water. The Arctic becomes filled with a quiet hum beneath the ice. These acoustic signatures allow scientists to map where methane hydrates are located. They listen to the ocean as if it were speaking in a language of clicks and pulses. Each sound is a clue. It tells them where the hydrate has begun to melt. It tells them where the gas is escaping from the seafloor. It tells them how the permafrost is changing in the dark. Sometimes the sound is brief, a simple burst of bubbles. Other times it continues for hours. It can come from cracks in the permafrost or from deep fissures in the seafloor. These sounds reveal the shifting state of the frozen ground. They show that even the most ancient parts of the ocean are never fully still. The methane hydrates beneath the Arctic are a reminder of time and change. They formed in ages that are long past. They have remained trapped for thousands of years. Now, as the conditions shift and the ocean warms, the frozen stores of methane begin to awaken. Subsea permafrost is no longer just a solid foundation. It is a dynamic layer that reacts to the world above and below. When probes descend into this world, they must tread carefully. Their presence alone can alter the fragile balance. They study the hydrates and listen to the acoustic signals that rise from the deep. The methane traps are both a treasure of scientific knowledge and a warning written in the language of ice. They tell the story of ancient seas and of a world where even solid ground can hold secrets in its frozen heart. Here, beneath the Arctic shelf, the The seafloor breathes in silence. The hydrates sleep until the balance changes, and when it does, they speak through the bubbles and sounds that echo through the water. In that quiet and ancient world, the frozen methane holds the history of Earth, waiting in the shadow of the ice. Far below the drifting ice and the cold ancient waters lies a boundary in the Earth itself. It is not marked on any surface map. It does not announce its presence with mountains or plains. It rests in darkness, hidden beneath miles of water and an unbroken shield of frozen sea. This boundary is the Gackle Ridge. The Gackle Ridge stretches across the deep Arctic basin like a seam in the ocean floor. It is a place where the Earth's crust is slowly pulling apart. Two tectonic plates, moving with a patience that spans millions of years, separate along this line. The movement is so slow that it is almost unimaginable. The Gackle Ridge is one of the slowest spreading ridges on the planet. The plates drift apart only by a few centimeters each year, yet this quiet motion has a powerful effect. It allows molten rock from deep within the Earth to rise toward the surface. When we imagine volcanoes, we think of fiery mountains and clouds of ash. We imagine explosions and glowing lava, but underwater volcanoes look nothing like this. They are silent builders. They release heat and minerals into the ocean in a slow and steady way. They form vents and fissures on the seafloor. They shape the chemistry of the water itself. For many years, scientists believed that the Arctic, with its cold and isolated ocean, might be too quiet for volcanic activity. The ridge was known, the tectonic plates were known, but few imagined that volcanoes could still be active under so much ice. Then, in the early 2000s, echoes from sonar and data from seismic sensors revealed something new. There were signs of eruptions along the Gackle Ridge. Not ancient eruptions, recent ones. Fragments of volcanic glass were found along the seafloor. These fragments form when molten lava cools rapidly as it meets cold water. They were not worn by time or covered by sediments. They were fresh. Researchers identified deep fissures that had released lava in quiet bursts. They saw evidence of vents releasing heat and minerals into the water. Small chimneys had formed where hot fluid met cold ocean, depositing minerals in strange shapes. These discoveries changed our understanding of the Arctic. The seafloor was not silent. It was alive with the slow and steady heartbeat of geology. Even in the coldest ocean on Earth, the planet continued its ancient work. Underwater volcanoes do not erupt in a single dramatic moment. They release heat and minerals in pulses. Some vents produce fluids so hot that they change the chemistry of the seawater around them. These fluids rise in plumes that drift upward through the dark. They carry metals and dissolved particles into the surrounding water. Where the plumes meet cold seawater, the minerals condense and fall like underwater snow. These geothermal vents create unusual environments. The water immediately around them can be many degrees warmer than the surrounding ocean. It holds chemicals that do not appear anywhere else in the deep Arctic. Microbes feed on these chemicals, turning them into energy. Entire ecosystems form around the vents, thriving in darkness and cold. The chemistry of the water in these places is changed by the volcanic activity. Metals dissolve in the heated water and travel through the currents. When the water cools, the metals form small particles that settle into the sediments. These particles become part of the seafloor. They carry the history of the vent. They show scientists where heat once escaped the Earth. The heat from the volcanoes also changes the temperature of the deep ocean. It warms the water in subtle ways. The warmth is not enough to melt the ice above, but it is enough to create pockets of different chemistry. It is enough to shape the movement of currents and the life that grows in the deep. The Gokul Ridge is one of the most mysterious ridges on the planet because it is so hard to reach. There are only a few places where submersibles have been able to explore. The ice blocks surface ships. The currents move unpredictably. The darkness makes navigation difficult. Most of the ridge remains unseen. Yet, even with limited access, the evidence is clear. The Arctic hides volcanoes beneath its frozen shield. These volcanoes do not roar or send ash into the sky. They release their energy into the water, altering the world around them in quiet ways. They shape the ocean floor. They feed the microbes that thrive near their vents. They keep the planet's geology alive beneath the cold. In this deep and ancient place, the Earth continues its work. The plates move, the magma rises, the water changes. The Arctic reminds us that even the quietest places on Earth hold the power of fire beneath their surface. In the deep quiet of the Arctic, even the stillness has a sound. It is not the roar of storms or the crackle of wind. It is the voice of the ice itself. Although it may appear solid and unmoving, the frozen surface is constantly shifting. It expands in the cold. It tightens under pressure. And sometimes, that pressure reaches a breaking point. When the ice fractures, the movement sends vibrations through both the ice and the water. These vibrations are known as ice quakes. An ice quake begins with tension building beneath the frozen roof. Pressure collects along lines where slabs of sea ice press against one another. The forces are slow and constant, the result of drifting plates and changing temperatures. When the stress becomes too great, the ice suddenly snaps. The crack can stretch for hundreds of feet, racing across the surface with astonishing speed. The sound of it, if you were close enough to hear, is sharp and deep, like thunder trapped beneath a frozen sky. These fractures do more than mark the surface. They generate seismic waves that travel through the ice, through the water, and even into the seafloor. The Arctic becomes an instrument. The vibrations move like ripples, spreading outward to reveal the strength of the break. Some ice quakes are small. They create only minor tremors. Others release forces powerful enough to register far from their origin. Underwater sensors detect the sudden pulse of energy. Seismographs record the signals as they move through the earth. Unlike earthquakes, these events are not caused by shifting rock. They are created by the movement of ice. The frozen surface responds to the same large-scale forces that shape the ocean it floats upon. The result is an ongoing rhythm of formation and collapse. The sound of these movements can travel for miles. Even in total darkness, instruments can detect the quakes as they echo through the deep. One of the most dramatic effects of these fractures is the collapse of pressure ridges. Earlier in our story, we explored how the movement of the ice creates towering walls where slabs collide. Over time, the weight of these ridges grows. The ice thickens as old layers press upward. These formations are strong, but they are far from stable. When a fracture cuts through the surface, these ridges can fall apart in massive collapses. Imagine a mountain of ice breaking loose and crashing into the sea. The collapse sends blocks of frozen water tumbling downward. The impact throws waves through the ocean. The disruption extends far beneath the surface. A submarine caught beneath one of these events can be struck by falling ice or forced out of a safe path. The water churns. The currents shift. The once familiar landscape of the deep becomes an obstacle course. These collapses do not always happen when expected. The ice moves in silence. The pressure builds slowly. A ridge that has stood for weeks or months may fall without warning. The danger lies in the unpredictability. It is difficult to know when the ice will break or where the cracks will form. A sudden shift can close a passage that was once open. It can create new obstacles or bury old ones beneath tons of frozen debris. For explorers who travel under the Arctic ice quakes are a serious threat. They can alter the environment in an instant. Submersibles must navigate through narrow corridors between ridges. A collapse can trap a vehicle. It can change the shape of the seafloor by pushing debris into valleys and channels. It can block escape routes or seal openings to the surface. Even if the submarine survives the shock, its path forward becomes uncertain. Ice quakes also create hazards on the surface. The crack can open wide enough to swallow equipment or destabilize research stations. The ice can shift so quickly that structures become isolated on drifting flows. The surface may split into huge segments that drift apart. The Arctic becomes a broken landscape of moving pieces. Each fracture is a reminder that the ice is alive with its own slow energy. Scientists listen to these quakes using sensitive instruments. They can measure the frequency and strength of the vibrations. Over time, the patterns begin to tell a story. They show how the frozen roof responds to the currents and winds. They reveal when the ice thickens and when it weakens. The quakes are signals from the Arctic itself. They are messages written in sound instead of words. Deep beneath the ice, the seismic waves of an ice quake move through water with remarkable clarity. They reflect from rocks and ridges. They travel along the seafloor. They tell scientists where the fractures occurred and how powerful they were. These signals help reveal the hidden changes happening beneath the frozen surface. Yet even with these tools, the ice remains unpredictable. The fractures come when the balance shifts. They reshape the ocean above and below. They create obstacles that were never planned for. The ice quakes are part of the silent drama of the Arctic. They are reminders that even the coldest and most remote places are never truly still. In this landscape of frozen motion, the ice can break with a single moment of release. The seismic waves travel outward, echoing through the ocean. The pressure ridges fall. The path forward changes. And the story of the Arctic continues, shaped by the quiet force of deep and ancient movement. If you listen to the Arctic, truly listen, you will discover that the ocean beneath the ice has a voice. It does not speak in a single language. It speaks in tones and pulses, in deep rumbles and high whistles. For decades, scientists and explorers have recorded sounds from this hidden world. Some have simple explanations. Others continue to puzzle researchers even today. These sounds have earned names: the bloop, the upsweep, the whistle, the ping. Each one is distinct. Each one tells a story that still feels unfinished. The bloop was first heard far away from the Arctic, a low-frequency burst detected in the 1990s by underwater microphones. It lasted only a moment. The sound was so powerful that it could be heard across multiple sensors thousands of miles apart. At first, it seemed like something enormous had moved deep within the sea. Some believed it could be a creature larger than any whale. Others suggested collapsing ice shelves or undersea geological activity. Years later, many scientists concluded that it most likely came from the fracture of large ice masses. Yet the sound remains a symbol of the unknown voices of the ocean. In the Arctic itself, other sounds have emerged. The whistle is a high-pitched tone that travels through the water and echoes beneath the ice. The upsweep is a rhythmic pattern of rising tones recorded each year during certain seasons. There are also short, sharp bursts like the ping, along with low hums that seem to vibrate through the entire basin. These sounds are recorded by hydrophones placed deep beneath the surface. The recordings show patterns, but not always explanations. To understand why these sounds feel so mysterious, It helps to think about how sound moves underwater. Sound travels farther in water than in air. It moves with more clarity. It reflects from surfaces and bends around obstacles. Beneath the ice, these effects become even more pronounced. The ice sheet above acts like a giant ceiling. It traps the sound, forcing it to travel along the underside of the frozen roof. Some sounds bounce from the ice to the seafloor and back again, gaining strength each time they reflect. This creates a strange and beautiful effect. A sound that begins in one place can be heard across vast distances. A single whistle recorded near Greenland might echo under the ice shelf and reach sensors near Siberia. Deep tones resonate like bells in a cathedral. High-pitched sounds drift like ghosts of vibration. The ocean becomes a chamber of echoes. Even the act of moving through this environment creates noise. The ice shifts and cracks, pressure ridges collapse, currents press against the frozen roof. The ocean itself is alive with motion, and each motion creates a sound. But there are other noises too, ones that do not fit neatly into the known rhythms of the Arctic. Scientists have suggested many explanations. Some point to volcanic activity along the seafloor. Underwater eruptions can create deep rumbling noises. Others point to shifting plates and small seismic events. Underwater landslides can send vibrations across the ocean. Some sounds may come from methane escaping the seafloor, bubbles rising in long and steady chains. These bubbles create a special acoustic signature, one that is sharp and rhythmic. Marine animals also contribute to the Arctic's underwater soundscape. Belugas and narwhals communicate using high-pitched calls. Bowhead whales produce songs that travel for miles. The presence of these creatures complicates the story. Sometimes their voices overlap with natural geological sounds. Other times, their calls become lost beneath the constant shifting of the ice. Yet even with all these explanations, some sounds remain a mystery. The upsweep is one of them. It began decades ago and returns each year during a specific season. It is composed of repeated rising tones. The source has never been identified. Some believe it is related to volcanic activity. Others suspect it could come from large sections of the seafloor shifting, and some think it might be created by currents moving beneath the ice, stirring the deep in ways we do not yet understand. There are also sounds that appear only once. They are detected on a single device. They last for only a moment, then they never appear again. These one-time sounds are the most difficult to study. They defy patterns and cannot be traced to a single cause. They might be fragments of ice quakes. They might be the collapse of underwater caves or the release of methane bursts. Or they might be something entirely different. Scientists continue to record and analyze these sounds. They build models to understand how noise travels under ice, how it reflects from ridges, and how it changes with temperature. They compare recordings over years and decades. Each new data set reveals a little more, yet what remains unanswered is just as important. The Arctic Ocean is one of the quietest and most echoing places on Earth. It is a natural amplifier for voices that come from the deepest waters and the most distant shores. The sounds remind us that the ocean is never silent. Beneath the frozen surface, there are stories too large for the eye to see. Some are geological, some are biological, and some are still waiting to be understood. The strange sounds of the Arctic continue to drift through the water, echoing against the ice and the seafloor, traveling farther than any human voice could reach. They are the unanswered questions, written in the language of the ocean, moving through a world where even silence speaks. In the frozen north, where the world narrows into a crown of ice and ocean, an invisible force twists through the water and sky. It is not something you can see or feel. It does not ripple the waves or shake the ground. Yet, every explorer who has ever tried to navigate the Arctic has encountered it. It is the quiet power of magnetism. Near the North Pole, the Earth's magnetic field warps and bends. It does not move in neat lines or point reliably toward a single direction. It curves into loops and folds into spirals. These distortions confuse compasses and instruments. What seems fixed and trustworthy elsewhere in the world becomes unruly beneath the polar sky. To understand this, imagine the Earth wrapped in a giant magnetic field. This field is created by the movement of molten iron deep within the planet. Most places on Earth feel the field in a smooth and predictable way. The compass needle points north and guides ships across oceans and land. But as you approach the pole, the magnetic field lines do not run horizontally along the surface anymore. They dive downward into the Earth. The compass needle tries to follow these lines. Instead of pointing forward, it tilts toward the ground. A compass that lies flat cannot tell the difference between north and down. The arrow shifts and wavers. It becomes slow and hesitant. Sometimes it spins in circles before settling on a direction that is not north at all. For centuries, early explorers were stunned by this strange behavior. Their tools betrayed them. Even the magnetic pole itself refuses to stay still. It drifts across the Arctic at a pace that has changed over the decades. Scientists track its movement like the migration of an invisible star. Some years it shifts only slightly, other years it moves quickly. It wanders across the ice and sea, guided by the currents of molten iron deep inside the Earth. Navigation charts must be updated again and again. Under the ice, the distortions become even stranger. Sound waves bounce and echo, pressure shifts, but magnetic forces remain powerful and quiet. They influence every metal object. They touch the sensors of submarines and research vehicles. A compass does not simply point in the wrong direction. It may refuse to settle. It may tremble as if trying to find a path through a maze. Underwater navigation depends on more than sight. It depends on instruments that track direction and movement. Some of these instruments rely on magnetic fields. Others rely on gyroscopes and accelerometers. When the magnetic lines begin to bend, these instruments face competing signals. A submersible may drift from its intended route without realizing it. Its path becomes a slow curve instead of a straight line. Oceanographers and engineers must plan for these distortions. They build systems that measure magnetic variation. They map the invisible lines that guide the field. They calculate corrections so that navigation remains possible. Yet even with modern tools, the Arctic holds surprises. A vehicle may reach a place where the magnetic field shifts abruptly. The instruments must adjust, or the machine will lose its way. The water itself can amplify these effects. Salinity and temperature change the way magnetic signals behave. In certain conditions, the ocean acts like a conductor. It channels the magnetic field in unusual patterns. The lines bend as they pass through deep currents or around volcanic ridges. They twist near large deposits of metal beneath the seafloor. The distortions become complex and unpredictable. In the past, sailors relied on the stars when compasses failed. They measured the height of Polaris above the horizon, but beneath the ice, there is no sky. There is no star to guide the way. Submarines must trust their instruments, even when the invisible forces surrounding them pull and twist. A wrong adjustment can lead to drifting into dangerous waters or sealed corridors beneath the frozen surface. The magnetic field is not only a navigational challenge, it is a reminder that Earth itself is alive in a way we rarely notice. Deep within the planet, Molten iron flows and spins. That movement shapes the magnetic shield that protects the world from solar storms and cosmic particles. Near the poles, these forces rise to the surface and make themselves known. Some scientists believe that the Arctic's magnetic distortions hold clues to the workings of the Earth's core. By studying how these fields shift over time, they hope to understand the powerful currents and heat deep below. They listen to the magnetic pulses like ancient sailors listen to the wind. In the Arctic, navigation becomes a conversation with the unseen. There is no single path or answer. The compass needle trembles and turns. The magnetic lines fold into curves around the pole. Machines must trust other senses. Under the ice, every direction becomes uncertain. Here, in the far north, the story of the Earth is written not only in rock or water, but in an invisible map of forces that guide the world. The magnetic field flows across the ocean and into the darkness. It touches every ship and submarine that enters this place. It does not shout, it whispers. And when the compass falters, the Arctic reminds us that some landscapes are shaped not by stone or ice, but by the silent pull of the planet itself. There are many ways to explore the ocean beneath the Arctic. Machines can dive, submarines can navigate, probes can measure and record. But to truly weave a path through this world, explorers must also find a way to speak across the distance. They must send messages, receive instructions, and stay connected to the surface. This is where the Arctic reveals yet another challenge. Beneath the ice, communication begins to fade. Near the poles, satellites lose their certainty. Most of the satellites that orbit Earth circle closer to the equator. Their paths allow them to see most of the planet, but at the very top of the world, their signals become unreliable. The satellites arc across the sky in patterns that leave long gaps in coverage. Some pass overhead only briefly. Others do not reach the poles at all. The higher the latitude, the less dependable the signal becomes. This is not just a matter of distance. The Earth's magnetic field bends high-energy particles toward the poles. These particles disturb the upper atmosphere and interfere with radio waves. The result is a quiet, shimmering disruption. The signals from satellites weaken and break apart. A message that travels across oceans and continents may reach the Arctic and disappear into static. Even modern communication networks struggle in this place. Above the ice, researchers have tried building ground stations and relay systems, but wind, snow, and shifting ice make it difficult. The surface changes too quickly. An antenna placed in one spot may drift miles away within a season. A fixed structure may become isolated or crushed by the movement of the ice. The Arctic reminds us that nothing here stays where we expect it to. So we look downward, into the ocean, hoping the sea might carry our signals. Underwater, radio does not travel well. Radio waves weaken rapidly as they pass through seawater. The salt and minerals absorb the signal and break it apart. A message that might travel thousands of miles through air dissolves within a short distance underwater. Even powerful transmitters cannot pierce the ocean for long. The deeper the signal travels, the weaker it becomes. Sound waves move more easily through the water, but they are not well suited for complex messages. They bounce and echo. They change speed as temperature and pressure shift. A simple command may become twisted into noise. A submarine beneath the ice must steer by instruments that do not rely on surface contact. It travels in a world where communication is more like whispering through layers of stone. Some missions use acoustic signals to speak in simple coded pulses. These signals can reach across long distances, but they cannot carry large amounts of information. A single instruction might take minutes to send, and as the signal moves, It reflects from the underside of the ice, and from the seafloor, it splits and spreads. The ocean becomes a hall of mirrors for sound. Explorers must listen carefully and choose their moments. Because of this, most submersibles rely on storing information and returning it to the surface later. They collect data in their memory like a traveler keeping notes in a journal. Only when they surface do they share the story they carried through the deep. But surfacing is not simple here. Openings in the ice vanish, pressure and weather change. The machine must search for a gap where it can rise and send its message. Over the years, researchers have attempted to build new ways of communicating beneath the ice. Some have launched autonomous underwater vehicles that relay messages from sub to sub, like a chain of messengers passing notes through a city. Others have developed special buoys that rest just below the ice, listening to acoustic signals and translating them into radio waves once they reach the surface. These experimental systems are still delicate. They must survive the shifting ice above and the cold water below. There have been attempts to place communication nodes into the seafloor, small stations built to listen and transmit when a vehicle comes near. But the deep ocean moves slowly and unpredictably. The ice shifts overhead. Even the most carefully measured plans can be disrupted. In recent years, engineers have begun to imagine more ambitious ideas: satellite constellations that orbit near the poles, underwater fiber lines that carry signals across the basin, networks of sensors and relay stations that move with the ice instead of resisting it. Each idea faces the same challenge. The Arctic is not a place where technology remains untouched. It is shaped by the cold and the currents. It demands solutions that adapt rather than conquer. Even with all these attempts, the simplest truth remains. Communication beneath the Arctic ice is limited not only by distance but by silence itself. The frozen ceiling blocks the world above. The water absorbs and scatters signals. The magnetic disturbances near the pole confuse instruments. It is a place where isolation becomes a natural condition. This blackout is more than a technical obstacle. It becomes part of the story of the deep. Machines must travel with caution. They carry their knowledge through darkness and return only when the world above allows it. Beneath the ice, every signal feels fragile, every message a reminder of the distance between the surface and the hidden world below. In this quiet ocean, communication is possible only in fragments. We listen, we send messages, we wait, and the Arctic holds its silence. As we continue moving through the hidden world below the Arctic ice, another truth becomes clear. Even the most powerful machines built by human hands are cautious here. Modern submarines, engineered to dive into some of the deepest oceans in the world, do not simply push their way beneath this frozen ceiling. They navigate it with hesitation. They choose their paths carefully. And there are places they avoid altogether. On the surface, a submarine looks like a vessel built for fearlessness. Thick steel hulls, advanced sonar, engines capable of traveling across entire oceans without stopping. Yet in the Arctic, strength alone is not enough. The design of a submarine creates limitations that are not always obvious. A submarine needs space above it. It needs room to move and to adjust its depth. Under a thick sheet of ice, these simple movements become dangerous. A submarine is built to surface through water, not through ice. The hull is strong, but it was never meant to break solid frozen layers. Even a few feet of ice can stop a submarine from rising safely. If the crew tries to surface without knowing what lies above, the entire vessel could become trapped. The hull might press against unbroken ice with no way to move higher. The submarine would be pinned beneath a roof that cannot be cut or lifted. The fear of surfacing into the wrong place has shaped underwater navigation for decades. The ocean beneath the Arctic is full of shifting openings and hidden chambers. A clear path one moment may become sealed in the next. A hole in the ice may close in silence. A submarine could become caught beneath a frozen barrier with no escape route. The pressure of the ice is slow and steady. It does not need force to trap a vessel. It simply forms above it and waits. The risk is not only the ice itself. There are places where the seafloor rises sharply. Underwater ridges and shallow shelves sit just below the surface. A submarine that strays into these regions could collide with the seafloor. Even with maps and sonar, this danger is real. The Arctic is not fully mapped. The seafloor changes and shifts. New obstacles appear where old maps show clear water. Navigation becomes a careful dance rather than a straight path. Some parts of the Arctic are avoided because of the unpredictable movement of the ice. Pressure ridges can form quickly, creating underwater walls that block the path. Ice quakes can collapse entire formations, sending debris into the water. These events create hazards that a submarine cannot always anticipate. Even a small collision can damage the vessel or break the delicate sensors that guide it. There are also places where the currents are too strong. We have already drifted through the world of the Arctic's internal ocean currents. Those powerful forces that flow beneath the ice can push a submarine off course. The machine may try to correct its path, but the water moves with a force that is difficult to resist. A submarine caught in the wrong current may be pulled toward places that are too dangerous to navigate. For these reasons, naval forces and research vessels chart safe corridors where submarines can travel. These are routes measured again and again. They are chosen because the ice is less dangerous or the water is deep enough to allow movement. Even then, the journey is watched with care. Crews monitor the thickness of the ice above and the contours of the seafloor below. They listen for the sounds of shifting ridges and cracking ice. Some parts of the Arctic are considered completely off limits. These are regions where the ice is too thick or where the water is too shallow. There are basins where the seafloor rises nearly to the surface. There are long stretches where no known openings exist. If a submarine traveled into these zones, it might never find a safe place to rise. Even a small change in direction could lead to entrapment. Military submarines have learned these lessons through a long history of Arctic missions. There have been moments when vessels came close to disaster, times when a submarine attempted to surface and found nothing but unbroken ice overhead, moments when sensors were confused by magnetic distortions and showed a clear path where none existed. These stories have shaped the rules that submarines follow, so modern vessels avoid these regions, not out of caution alone, but out of understanding. The Arctic is vast and powerful. It does not bend to human technology. Even the strongest hulls do not guarantee safety here. The ocean beneath the ice demands respect. It asks explorers to learn its paths and listen to its movement. Submarines that travel through this world must carry more than engineering. They must carry patience. They must follow the safe routes that generations of sailors have mapped. They must choose where to surface with care. They must navigate by more than instruments. They must understand that there are places where no machine should go. In this silent ocean, the limits of technology are clear. There are regions where a submarine can glide through open water. There are places where it cannot go at all. And between them lies the Arctic, unchanged by our presence, reminding us that even our most advanced vessels have boundaries drawn by nature itself. As we move deeper into this hidden ocean, another strange phenomenon reveals itself. It does not come from shifting ice or ancient currents. It is born from the quiet ways that temperature and water interact. The Arctic holds a mystery of sight, not for human eyes, but for the instruments we use to see in the dark. Sonar is the primary sense of every machine beneath the ice. Where light cannot travel, sound must take its place. The pulses of sonar travel through the ocean, bounce from objects, and return as echoes. From these echoes, machines draw a map of the world. They tell the shape of mountains, the distance of ridges, and the location of passages that lie hidden beneath the frozen roof. But in the Arctic, sound does not behave the way we expect. The ocean forms thermal layers, thin bands of water that differ in temperature. These layers are invisible to sight and impossible to touch. Yet, they are powerful enough to bend sonar waves. The Arctic behaves like a giant lens, not of glass but of water. This is the reverse lens effect. Imagine sending a sound wave forward, expecting it to travel straight ahead. Instead, when it meets a layer of water that is slightly warmer or colder, it changes direction. The wave bends. It dips downward or rises upward. It curves as if pulled by some unseen force. A submarine might believe it is scanning the ocean floor, when in reality, its sonar beam has slipped and is now sweeping across the middle of the water column. Or it may aim for open water and find the sound reflecting back from a ridge it has never seen before. Layers of different temperature are common in every ocean. But in the Arctic, these layers are sharp and sudden. They form where warm currents meet the cold. They settle beneath the ice like thin sheets of glass. The sound that travels through these layers becomes unpredictable. One small change in temperature can shift the direction of the wave by a surprising amount. The result is a map that lies. When sonar is bent by thermal layers, it returns echoes from objects that are not where they appear to be. A submersible might detect a ridge many meters away from its true position. It might see the shadow of a cave that is not directly in front. These distortions are known as ghost images. A ghost image can look exactly like the real world. It can show a clear outline of a large object. It can mimic the shape of a seafloor cliff or a drifting iceberg. But the image has shifted in space. It may sit higher or lower. It may stretch across the water like a mirage. The machine reading the sonar believes the image is real. It does not know the ocean has changed the angle of its vision. In some cases, multiple layers bend the sound in different ways. The echo bounces through several bands of water before returning. The path twists. By the time the sound reaches the submarine, the echo has created a false landscape. Mountains appear where the ocean is flat. Empty corridors become walls. Cliffs fade into deep valleys. The Arctic becomes a place of illusions. The reverse lens effect is not limited to sonar. It also affects the echo of underwater sounds. A distant crack in the ice may sound close. A falling ridge may echo far from its origin. Navigation and communication become more complicated. The ocean reshapes itself in sound. For submarines and research vessels, this phenomenon is not merely a curiosity, it is a danger. When machines believe the ghost image, they may steer into the wrong path. A safe route can become a dead end. A dangerous obstacle may seem to disappear. Pilots must learn to read the distortions. They must learn to question what the instruments show. Scientists have studied the Arctic reverse lens effect by releasing sound pulses and tracking their paths. They map how the waves bend in different temperature layers. They measure the speed of sound in water that is only slightly warmer or colder. With each experiment, the picture becomes clearer. Temperature differences of even a few degrees can bend sound enough to change the shape of a map. To understand the effect more deeply, think of light passing through glass. When light enters a lens, it bends and forms an image that may be larger or smaller. Water behaves similarly with sound. The Arctic is a giant lens made of layers. The image it creates is not always true. Machines do not see directly, they see through echoes and reflections. They rely on the ocean to deliver their senses. And the Arctic, with its shifting waters and thermal boundaries, answers with curved paths and ghost images. In this deep and quiet world, even sound must learn to move carefully. It must navigate the hidden layers of temperature beneath the ice. It must follow paths that twist and turn through the water. And through these distortions, the Arctic reminds us that vision is more than sight. It is a conversation between what we expect to see and what the world chooses to reveal. There is a belief shared by many who look at the Arctic from far away. As the Earth warms and the ice melts, the region should become easier to explore, fewer frozen barriers, more open water, greater access to the deep. But the truth of this place is more complicated. Climate change does not clear a path. It reshapes the world into something less predictable, something more dangerous. Seasonal ice once followed a rhythm. Winter froze the surface. Summer softened it. The transitions were steady and slow, but as temperatures rise, that rhythm breaks apart. The ice no longer forms in the same patterns. The melt begins earlier or later. The seasonal boundaries blur. Ice becomes unstable in ways that make planning impossible. Some areas of the Arctic that once remained frozen throughout the year now experience partial thaw. The top layers of ice weaken. Cracks form where none existed before. The ocean absorbs heat. It pushes warmth into the underside of the ice. The result is a surface that looks solid but trembles beneath the weight of change. This instability poses new threats. A research vessel or a submarine might rely on a region of first-year ice for shelter or navigation. But the ice does not remain steady. It softens during a brief warm period. It fractures under pressure. The open water beneath transforms the ice into thin sheets that drift quickly. The frozen roof becomes unpredictable. It can move faster and scatter in unexpected directions. One of the most troubling changes is the increase in sudden freeze events. These events occur when warm air or water is followed by a rapid drop in temperature. The ocean surface can freeze almost instantly. A submarine traveling through open water may find itself trapped beneath a new layer of ice only hours later. Escape routes that were open at dawn may be sealed by nightfall. These sudden transformations also affect the movement of ships on the surface. A vessel may be surrounded by a ring of water one moment and locked in ice the next. The freeze can happen quietly, without warning. The wind shifts. The temperature falls. The sea becomes a field of crystal plates that link together in silence. The ship is held in place by the frozen world. It waits for the ocean to shift again. The opposite is just as dangerous. Warm currents push through from lower latitudes. They melt the ice in jagged patterns. Open water stretches across the Arctic where none used to exist. But the open water brings storms. With fewer ice sheets to calm the waves, the sea becomes more violent. Swells form in places where the ocean was once still. These storms throw the ice into motion. Strong winds push it against ships and structures. The sea becomes a battlefield of water and frozen blocks. As the climate changes, new hazards emerge. Meltwater pools collect on the surface of the ice. These pools, blue in color, glimmering beneath the Arctic's SON, weaken the ice below. They carve channels that guide meltwater into deeper layers. The Arctic becomes riddled with these pockets. A vehicle crossing the ice may sink into these pools or crack the surface beneath. The melting of sea ice also exposes parts of the coastline that were once protected. Waves erode the land, sediments shift, new underwater obstacles form. Once familiar passages become shallow or blocked. Submarine routes must be recalculated again and again. Instruments that once relied on stable maps must adjust to a changing landscape. The rapid melt patterns also reveal another challenge. As ice thins and retreats, it no longer acts as a steady platform for scientific work. The ground stations used to collect data must be moved or abandoned. Buoys that measure water depth or temperature drift away with the ice. Even the simple act of placing equipment on the surface becomes a hazard. For those who explore the Arctic, change becomes the constant. They must plan for shifting ice sheets. They must expect storms where calm once existed. They must prepare for rapid freeze and rapid melt. The world they enter is no longer steady. It has become an ever-changing mosaic of frozen and liquid water. Climate change does not simplify the Arctic. It makes the region more dynamic and challenging. The ancient rhythms of the ocean and ice give way to new patterns shaped by warmth and speed. The environment transforms itself in hours instead of seasons. Explorers cannot rely on past knowledge alone. They must listen to the present. In this era of transformation, the Arctic becomes a landscape of motion. The ice breathes and shifts. The sea rearranges itself. Each journey demands more caution and more understanding. The melting world of the Arctic creates new paths only to close them again. It invites explorers inward and then guards its depths more fiercely than before. What was once frozen becomes unstable. What was once predictable becomes wild, and the Arctic continues to remind us that its mystery is not softened by change. It becomes deeper. Scattered across the Arctic, beneath the drifting ice and along the frozen coasts, lie remnants of a different age. They are not fossils or ancient bones. They are pieces of human history. Relics of wooden ships and iron tools, abandoned shelters, forgotten cargo. They rest in the quiet cold, where time moves more slowly. And because of that, many of them remain untouched by decay. For centuries, explorers tried to cross or conquer the Arctic. They came in long wooden ships, guided by compasses and hope. They believed in a passage through the frozen sea. They believed the Arctic could be mapped and mastered. Some returned with stories and discoveries. Others remained behind, swallowed by the very ice they hoped to escape. The cold does something rare here. It preserves. When something falls into the Arctic, it can remain frozen in place for decades or centuries. Wood does not rot. Fabric does not crumble. Metal does not rust as quickly. The ice becomes a vault, hiding these artifacts beneath thick layers of freeze. They wait like memories suspended in time. Many of the most famous relics come from ships that became trapped and were abandoned. The crews hoped the ice would release them when the weather warmed, but the Arctic does not always return what it takes. Some ships were crushed by the shifting flows. Others sank beneath the surface. Their remains now rest on the seafloor, still shaped by the craftsmanship of the past. One of the most haunting examples is the fate of early 19th century expeditions. Explorers set out to map the Northwest Passage, believing it was a gateway to distant trade routes. Their ships became locked in ice. They drifted for months or years before vanishing. For generations, the world did not know what had happened to them. Only recently have explorers found their remains using modern techniques, discovering entire structures preserved by cold. Metal cannons and anchors lie in their original places. Wooden beams sit nearly intact. Plates, bottles, and tools lie scattered across the seafloor as if someone had just set them down. Some cabins still hold personal belongings: a watch, a spoon, a pipe. These objects tell a story of survival and uncertainty. They show a world where the cold claimed everything slowly and completely. Along the frozen shores, the relics are not only ships but campsites left behind, stone shelters that once protected crews during harsh winters, food caches buried beneath rocks, clothing and equipment that remained undisturbed for generations. The Arctic preserved these things quietly. It kept them hidden until explorers returned to find them again. Ice acts like a perfect container. When a ship sinks in cold water, the temperature slows the decay. Sediments settle slowly. Marine life cannot damage the structure as quickly. Even the paint and markings on some artifacts remain visible. Time becomes gentle here. The world pauses. There are also relics that have been trapped in the ice itself. Sometimes a storm or a shifting flow carries objects across the ocean. They become embedded in the frozen surface. Tools, ropes, fragments of sleds. The ice moves them across the Arctic like quiet travelers. They drift for years before surfacing on distant shores. They tell the story of human movement through a place where people rarely stay. Modern science uses these relics to learn about the past, not only about explorers, but about the climate they faced. The wood used in ships tells where they were built. The metals show the technology of the time. Some objects reveal how crews adapted to the cold. They show methods of travel and survival. They hold clues about the challenges faced by those who entered this world long before sonar, satellite, and steel. Archaeologists treat these finds with care. They understand the ice does more than preserve objects, it preserves stories. A ship trapped by ice tells of earlier seasons when the Arctic froze in different patterns. A camp abandoned in haste shows how quickly the environment changed. Even the arrangement of tools and supplies speaks of the urgency and hope that guided early explorers. Many of these discoveries remain deep beneath the ocean, unreachable to most. They are protected by layers of cold and darkness. They rest in silence, kept safe from storms and time. Others lie on shorelines where the ice has retreated. They wait in the sunlight, rusting only slightly, still bearing the marks of the people who used them. These relics remind us that the Arctic has always been a place of curiosity and risk. They tell of journeys across uncharted waters, of decisions made in the face of cold and darkness. They show the courage and the uncertainty of those who believed they could cross the frozen sea. They preserve the dreams and the failures of human exploration. The relics do not speak. They remain still in the ice, but they hold the past in perfect silence. In their presence, we remember how long the Arctic has drawn explorers into its mystery, and how gently it keeps their stories frozen in time. Even the most advanced technology has difficulty entering the world beneath the Arctic ice. Humans can plan, design, and build machines capable of surviving crushing depths and enormous pressure. Yet the Arctic does something to these machines that few other places on Earth can. It challenges every moving part. It resists electricity and mechanical strength. It slows the pulse of the robot until it fails. This battle begins with something simple: cold. Not ordinary cold, but cold that settles deep into every material. When a robot moves through water that is near freezing, the chill reaches into its joints. The metal contracts and stiffens. Moving parts become less flexible. Lubricants thicken and clump, slowing motion, Motors strain, hinges creak. The machine begins to resist itself. In some cases, the joints freeze completely. Ice forms where water collects on metal surfaces. Tiny layers of frost appear inside the mechanisms. Even a thin layer of ice can stop a robotic arm or a spinning thruster. The machine becomes stuck, unable to move or change direction. It waits in the darkness because nothing around it will thaw. The Arctic holds it motionless. The cold affects more than the joints. It influences the power source. Batteries, which seem so reliable on land, fail rapidly in the Arctic. Chemical reactions inside the batteries slow down as temperatures drop. The battery cannot release energy quickly enough. The power fades. The lights dim. Sensors stop responding. A robot built to travel hundreds of meters might lose power after only a brief time beneath the ice. Some instruments use heaters to keep batteries warm, but heaters require energy as well. The robot must use some of its strength simply to protect itself. The longer it stays beneath the ice, the more energy it loses. The machine faces a choice between survival and exploration. It can move deeper into the Arctic, or it can preserve what little power remains. The cold creates one more problem that machines must face. Water condenses inside delicate systems. Even a small drop of moisture can damage electrical circuits. Wires corrode, sensors stop functioning. The ocean seeps into places it should never reach. Engineers build tight seals to protect the electronics, but seals can crack in the cold. Pressure pushes against every edge. The slightest flaw becomes a weakness. Then there is the weight of the ice itself. A robot beneath the surface navigates in a narrow space. It must keep a safe distance from the ice roof above and the seafloor below. It must avoid becoming trapped. It must watch the currents and the changing conditions. Under-ice robots need sensors that can see in directions that humans do not think about. They cannot rely on vision alone. They must sense the world through sound and motion. This is why some of the earliest underwater vehicles struggled in the Arctic. They were not built for the complexity of this environment. They moved through the deep ocean, but failed in narrow places beneath the ice. Their power faded, their joints froze, their sensors broke down. The ice became a barrier that was not physical, but mechanical. Despite these challenges, engineers have not given up. They continue to design machines that can survive longer and dive deeper. One of the greatest breakthroughs came from studying how nature survives the Arctic. Scientists examined fish and microbes that thrive in the cold. These organisms produce special proteins that keep their cells from freezing. Inspired by this, some robots now use antifreeze-like fluids inside their moving parts. These fluids remain liquid in freezing temperatures. They protect joints from seizing. Another breakthrough came from finding new energy sources. Some modern underwater robots use battery chemistries that resist cold. Others carry small power systems designed to keep the internal temperature stable. Engineers study every failure. Every lost machine becomes a lesson. Each malfunction helps build a better design. There are also new methods for communication. Instead of radio, which cannot travel far underwater, some robots use acoustic signals. Others leave relay points along their path, small devices that help transmit data back to the surface. These systems allow robots to move further from ships and research stations. They explore deeper into places where no human could guide them. Some technology uses buoyancy instead of mechanical movement. These robots change their weight to rise and fall in the water. They do not rely on propellers or thrusters that can freeze. They drift with currents and adjust their motion softly. These vehicles conserve energy and survive longer in the Arctic's dark. There are even machines that are designed to work with the ice rather than against it. They glide along the underside of the frozen roof. They use the smooth shelter of the ice to guide their path. They scrape tiny layers of frost away from their joints and protect themselves from cold seawater. They search for cracks and tunnels where the ocean opens into hidden spaces. Each step forward in robotics is small. A little more endurance, a little more protection, sensors that last longer, batteries that hold their charge, joints that move even when the water freezes. The battle with under ice robotics is not a story of defeat, it is a story of patience. The Arctic does not give away its secrets easily, yet the machines we send into its depths continue to return with fragments of knowledge. They send back images and data. They discover vents, currents, and ancient water. They move deeper each year, shaped by everything they learned from the cold. The ice may resist, but the machines keep trying. And slowly, the Arctic lets them in. Near the boundaries of the frozen roof, where the solid world of ice meets the dark water below, life gathers in quiet and surprising ways. The edges of sea ice are not empty. They are not silent. They are alive with organisms that have learned how to survive in a realm where sunlight rarely reaches and warmth is a distant memory. Along the underside of the ice, algae grow in flat green sheets. They cling to the frozen ceiling with delicate threads. These algae capture the faint light that filters through the ice in summer. When the sun returns for a short season, the ice itself glows with a soft radiance from below. The algae begin to bloom. They release oxygen and draw nutrients from the water. They become the first link in a food chain that stretches into the darkness. Small crustaceans gather to feed on this algae. Tiny shrimp-like creatures called amphipods drift along the ice edge. Their bodies move gently in the water as they collect the drifting particles. They swim in slow arcs and spirals, following the uneven patterns of light that seep down from above. These creatures have adapted to live in water that is near freezing. Their bodies hold natural antifreeze. Their cells and membranes resist the cold without breaking. These small animals attract larger ones. Fish swim through the dim space between water and ice. Some use bioluminescence to communicate or confuse predators. Others drift silently and let the currents carry them. Arctic cod is one of the most common fish beneath the sea ice. It moves in loose schools, feeding on the tiny crustaceans that follow the algae. The cod is not large, but it is important. It is a foundation of the Arctic ecosystem. To survive in near total darkness, Arctic cod does not search for sunlight. Its body senses vibrations in the water. It detects movement and sound instead of color. Its blood contains proteins that function even in freezing temperatures. Its muscles stay flexible, and its heart continues to beat in cold water. These fish are not simply surviving. They are thriving in a world that would be deadly for most others. Even larger creatures depend on the life that hides beneath the ice. Seals dive through narrow openings to reach the underside of the frozen roof. They move easily through the water, chasing fish or searching for crustaceans. They swim along the ice edge as if following an invisible path. Every breath, every movement is part of a larger rhythm that connects the surface and the sea below. In deeper waters where light never reaches, the life becomes stranger. Some fish have large eyes adapted to catch even the smallest flicker of light. Others have no eyes at all. They rely on touch and sound to find food. They move slowly, conserving energy in a world where every calorie matters. Their bodies are shaped by the cold. They are designed for silence and patience. Microorganisms live in the cracks and channels of the ice itself. They survive in pockets of salty water that do not freeze. These microorganisms form small communities. They feed on minerals. They drift with the slow movement of the ice. They show that life can find a home even in places that seem too harsh or too quiet for growth. There are jellyfish beneath the ice, too. Their translucent bodies drift through the water like pale lanterns. They glow with bioluminescence, creating soft flickers of light. These displays are not meant to attract sunlight. They are signals in the dark. They create a quiet language that belongs only to the deep. The creatures under the ice do not rely on sunlight the way most ecosystems do. They take energy from the algae that bloom when light returns. They find food along the ice edge. They draw strength from chemical reactions that take place in the water. Some feed on bacteria that survive near underwater vents. Others rely on the remains of ancient life that drift downward from above. Life here is slow and deliberate. Movement is measured. Growth follows the pace of the cold. Everything is adapted to endure long periods without sunlight. The Arctic does not rush. Its ecosystems breathe and flow with the turning of the seasons and the changing of the ice. The ice edge, the dark water, and the deep ocean form a single living system. What seems barren is rich with hidden activity. What seems empty is full of delicate networks. Beneath the frozen surface, life finds a way to grow without sunlight. It does not fade when the darkness returns. It simply shifts and waits for its moment. The Arctic shows that life can thrive in places where warmth and light are rare. It teaches us that survival takes many forms, and beneath the ice, the world continues to breathe quietly in the cold. In the dim world beneath the Arctic ice, light takes new forms. Sunlight is often too weak to reach this realm for most of the year, so the ocean finds its own ways to glow. It becomes a theater of faint sparks and drifting lights. Creatures that call this place home have adapted to darkness not by hiding from it, but by becoming a part of it. Bioluminescence is the light made by living organisms. It is not reflected from the sun. It is produced inside their bodies. In warmer oceans around the world, this glow is familiar. Some species shine brightly in waves or drift like tiny lanterns in tropical waters. But the bioluminescence of the Arctic is softer. It is quieter. It appears in brief moments and then disappears again. Many of the organisms that shine in these cold waters are small. Tiny plankton float through the water and respond to movement with a spark of blue light. These flashes come from chemical reactions inside their cells. The reaction is quick and delicate. It protects them from predators. It signals other organisms. It is communication in the dark. Some jellyfish glow as well. Their bodies drift with the currents, and they carry light with them. They shine like ghostly orbs as they move through the water. Their bioluminescence is a soft blue or green. It outlines the shape of their bodies and highlights their tentacles. They use this glow for different reasons. For some, the light attracts prey. For others, it deters predators. Many cold water organisms use bioluminescence to confuse larger animals that hunt them. When a predator approaches, they flash and vanish. The light becomes a distraction. It spreads through the water like a small explosion. The predator loses track of its target. The prey slips into the dark once more. Even some fish beneath the ice produce their own light. Their bodies carry organs that create bioluminescence. These organs form patterns that help fish recognize each other. They signal movement and direction. Instead of relying on sight, these fish speak through light and vibration. In a world where sound travels far and color fades, light becomes a language. One of the most fascinating things about bioluminescence in the Arctic is how rare it can be. Scientists do not see these glowing displays all the time. They appear briefly and then vanish again. Sometimes they occur when a submarine passes through the water. Other times the glow appears beneath a thin layer of ice. The flashes are quick. They are easy to miss unless you know where to look. During certain nights in the Arctic summer, when the ice begins to shift and break, the water beneath can shimmer. The movement of currents awakens the organisms. They glow in arcs and spirals. It looks like the northern lights reflected in the sea. These events are rare and unpredictable. They take place only when conditions are just right. Bioluminescence serves another purpose in this environment. It becomes a guide. In the darkness, creatures follow the signals left behind by others. They trace the paths of glowing organisms and find food or shelter. The light marks trails and hidden spaces. It reveals shapes and outlines in a world where nothing else can. During deep exploration beneath the ice, submarines have captured footage of glowing organisms drifting past. Some appear like stars, others resemble ribbons of light. There are moments when the ocean looks like a night sky. Tiny points of brightness shine in the darkness as if floating in air instead of water. There are also species that glow only when touched or disturbed. They wait in stillness until something brushes against them. Then they answer with light. This reaction spreads through groups of organisms like a slow wave. It shows the presence of movement. It reminds us that the Arctic is never empty. Even in complete darkness, it holds its own quiet constellations. Scientists continue to discover more about why Arctic organisms produce light. Some use it to attract mates, others use it to hunt, some use it simply to survive. The chemical processes that create this glow are complex. They involve proteins and reactions that take place deep inside cells. These reactions evolved over millions of years. They show that life always finds ways to adapt to the environment it inhabits. The bioluminescence of the Arctic is more than a survival strategy. It is part of the story of this place. It shows how life transforms darkness into something creative and beautiful. It shows how organisms use light to communicate, protect themselves, and explore. In the coldest and most silent corners of the ocean, these glowing creatures drift through the water. They shine softly and briefly. They move through a world without sunlight and create their own brightness. It is a reminder that even in places where light cannot reach, life still finds a way to glow. Far below the drifting ice and the silent world of deep water, another landscape waits. It does not move to the rhythm of currents or depend on sunlight or cold. It belongs to the ancient foundation of the earth itself. The seafloor of the Arctic is not smooth or predictable. It is covered in fractures and ridges that stretch across the ocean floor like the lines of an old and forgotten script. Much of the Arctic seafloor was unknown for centuries. Darkness and ice kept it hidden. Only in recent decades have researchers begun to map it using careful measurements and remote instruments. What they discovered surprised them. The fractures beneath the ice do not always follow the patterns found elsewhere on the planet. They appear in places that should be stable. They cut across the ocean floor as if something powerful once shifted the earth from below. These fractures show how the ocean basin formed long ago. They reveal where the Earth's crust tore apart and new rock emerged. In some areas, the cracks stretch for hundreds of kilometers. They create deep valleys and steep cliffs beneath the water. Sediments collect in these fractures. Over time, these sediments become a record of the ocean's history. They show how water, minerals, and life shaped the Arctic over millions of years. There are places beneath the ice where these fractures form unusual structures, Sharp ridges rise from the seafloor. They almost look like the spines of ancient mountains. They are remnants of old tectonic forces. The earth pushed these rocks upward and left them standing beneath the ocean. When instruments send sound waves across the seafloor, the echoes reveal these shapes. They create images of a world that has not seen sunlight for millions of years. The geological story of the Arctic also includes fragments of ancient continents. These fragments are pieces of rock that do not belong to the ocean floor. They come from places that once stood above water. Over time, the continents drifted and collided. They broke apart and formed new shapes. Some of these pieces sank beneath the ocean. They now rest under the Arctic, far from where they began. Scientists have found these fragments scattered across the seafloor. They are older than the surrounding rock. They carry minerals that match distant places on land. Some fragments may be part of ancient supercontinents that existed long before modern landmasses formed. They are like pages torn from an old book and misplaced in a new one. Their presence beneath the ice reveals how much the planet has changed. These discoveries raise questions. Why did these fragments end up here? What forces moved them? How did the Arctic basin itself form? The answers lie in the movement of tectonic plates. These plates are enormous pieces of the Earth's crust that shift and drift on the mantle below. They move slowly, but over millions of years they reshape the planet. They create oceans, mountains, and rifts. The Arctic does not follow simple rules of geology. It is a place where the plates meet in unexpected ways. Some parts of the seafloor show signs of spreading, where new crust forms. Other parts show compression, where plates push together. The pattern is complex. It suggests the Arctic basin evolved through many stages. It hints at earthquakes and volcanic activity long ago. The ridges and fractures beneath the ice are like scars from these ancient events. These formations have more than scientific importance. They help us understand the history of the Arctic. They show how the ocean basin trapped ancient water and shaped currents. They help explain why the seafloor holds geological features that influence life above. Some fractures become pathways for cold water to travel. Others allow minerals and heat to escape from below. They contribute to the unique chemistry of the Arctic Sea. Sometimes, geological formations beneath the ice hint at mysteries that are not fully understood. There are places where the rock appears cut or shifted in ways that do not match known tectonic processes. There are ridges that seem too young or valleys that seem too deep. Instruments reveal strange patterns. Researchers build theories and test them. The seafloor remains quiet and patient, holding its answers. Continental fragments tell a similar story. They show where land once connected in ancient times. They show how continents broke apart and drifted into new shapes. They remind us that the Arctic was not always a frozen ocean. It was once part of a different world, a warmer world, a world where plants and animals lived on land that now lies beneath the sea. The seafloor beneath the Arctic is more than a foundation. It is a record of time. It marks the movement of molten rock and solid crust. It holds the memory of storms and eruptions. Each fracture and ridge tells a story. Together, they form a map of the Earth's slow and quiet transformations. As we learn more about these geological formations, we see the Arctic not just as ice and water, but as a place shaped by forces far older than the cold. It becomes a reminder that beneath every ocean there is a history carved in stone, a history that waits for those who listen. Beneath the Arctic lies a world of memory, not the memory of machines or explorers, but of the Earth itself. On the seafloor, far below the drifting ice and darkness, layers of sediment have built up over thousands of years. They have settled there like pages in an ancient book. Each layer contains traces of the world that once was, tiny particles from distant lands, the remains of microorganisms, fragments of minerals and sand. The ocean holds these pieces gently, pressing them together over time. These sediments are chemical records. They tell the story of climate and ocean currents. They show when the Arctic was warmer or colder. They reveal moments of great change and long periods of stillness. Scientists study these layers because they hold clues about Earth's past that cannot be found anywhere else. To understand how this record forms, imagine a quiet snowfall. Each flake falls and settles on the ground. Then another layer forms on top of it. Over time, the snow becomes thicker. The oldest flakes rest at the bottom. Sediments in the Arctic work in a similar way. Particles drift down from the surface. They settle on the ocean floor. They form layers that grow year after year. Some layers come from distant rivers that carried minerals into the sea. Some come from organisms that lived and died beneath the ice. Others come from volcanic activity deep below the ocean. Each layer is different. Each holds its own story. Together they reveal how the Arctic has changed through the ages. Inside these sediments are chemical signatures. These signatures act like markers. They show when the ocean had more oxygen or less. They reveal when fresh water from melting glaciers changed the balance of salt in the sea. They show when volcanic eruptions spread ash through the water and settled into the deep. Isotopes inside these layers tell scientists when temperatures shifted by even small amounts. The presence of certain elements hints at storms, droughts, or changes in wind. The more researchers learn to read these signals, the more the seafloor becomes a history book written in minerals and dust. Despite the importance of these sediments, retrieving them is difficult. The Arctic guards its secrets. The deep water is cold and dark. The ice above is thick and unstable. Reaching the seafloor requires careful planning. Instruments must drill into the ocean floor without disturbing the layers. Each piece of sediment must be collected without mixing with modern water or other materials. Contamination is a constant concern. The slightest touch can change the chemical makeup of a sample. A single drop of warmer water or a small amount of oxygen can alter the record. The sediments are delicate. They require careful handling. Scientists often work slowly and with great precision. They use special tubes to collect cores from the seafloor. These cores are long cylinders of sediment. They show the layers clearly, from oldest to newest. Even once retrieved, the samples must be protected. They are kept cold. They are sealed away from air. Scientists examine them in laboratories designed to prevent contamination. They measure the chemical signatures and build a timeline of events. It is a slow and detailed process. Each piece of data is a small fragment of a larger story. These chemical records tell us not only about the past, but also about the future. The patterns in the sediment show how the Arctic responded to changes in temperature. They show how fast the ice grew or melted. They reveal how ocean currents shifted when conditions changed. By studying these patterns, scientists can make predictions about what might happen in the years ahead. The sediments also show how the Earth reacts to long periods of warming or cooling. They remind us that climate change has happened before, and the planet responded in complex ways. Some changes were slow, others were sudden. The Arctic has seen many climates, from warm oceans filled with life to frozen seas that stretched across continents. These records help scientists understand the relationship between the Arctic and the rest of the world. They show how events in the far north influence weather and ocean currents thousands of kilometers away. They help us see the Earth as a single connected system, A change in one place can ripple across the globe. The sediments beneath the ice are more than just layers of rock and sand. They are the memory of storms and seasons. They hold the history of water and life. They show how the planet breathes and shifts. They offer a glimpse of the Earth's hidden story. As we learn more from these chemical signatures, we begin to see patterns that stretch beyond the past. We see the beginning of something that continues today. The Arctic keeps its history in silence, but the ocean floor holds the answers for those who listen carefully. When we think of the Arctic, we often imagine a remote and isolated place, a region far from cities and forests, a world of cold and silence. But the Arctic is not separate from the rest of the Earth. It is connected to every ocean and every wind. It plays a larger role than almost any other place in shaping the climate that surrounds us. It is a global engine, always running in the background. The ocean currents that flow beneath the ice are part of a vast circulation system that spans the planet. Warm water travels from the equator toward the poles. When it reaches the Arctic, the cold air cools the surface. The water becomes more dense and sinks. It moves downward and spreads across the ocean bottom. This circulation acts like a conveyor. It carries heat, salt, and nutrients through the sea. These currents help balance the temperature of the Earth. Without them, the equator would be hotter, the poles would be colder, the climate would become unstable. The Arctic helps control this balance. It keeps the ocean moving. It guides the flow of warm and cold water. This flow affects the weather throughout the world. The Arctic also plays a role in the atmosphere. Cold air from the north moves south in wide patterns. It brings cool winds and changes pressure systems. Storms and calm weather both begin in the Arctic. The ice above the water reflects sunlight. It keeps heat from being absorbed into the ocean. When the ice melts, the dark water collects warmth. It changes how the atmosphere above reacts. It changes how clouds form and how storms move. Even the seasons are influenced by the Arctic. In winter, cold air spreads south and shapes the weather of distant continents. In summer, the melting ice releases moisture. This moisture becomes clouds that drift across the world. The Arctic acts like a center for global weather. It sends signals outward that the rest of the Earth responds to. The depths of the Arctic are important for another reason. They hold water that has been isolated for many years. This deep water stores heat and carbon. It moves slowly, almost like a hidden river beneath the sea. When this deep water rises, it releases heat to the surface. It changes the temperature of the region. It affects the circulation of the whole ocean. Understanding the Arctic means understanding how heat and cold travel through the Earth. It means learning how the ocean breathes. The ocean does not simply move. It exchanges gases with the atmosphere. It takes in carbon dioxide. It releases oxygen. It transports heat and salt. The Arctic is one of the main places where these exchanges happen. Scientists study the Arctic because it helps them understand the future of the climate. The patterns found in the Arctic depths show what might happen if the currents slow or change direction. They show how fast the ocean will warm if the ice continues to melt. They show how rising temperatures affect weather far away. One of the most important questions is how climate change will change the Arctic itself. If the currents weaken, warm water might not travel north as easily. The ocean could become more still. This stillness would trap heat in different parts of the world. It would change rain patterns, storms, and wind. It would affect crops and weather systems thousands of kilometers away. If the ice continues to melt, the Arctic will absorb more heat. The cold water will not sink as easily. The conveyor belt of currents could slow down. the deep ocean could become warmer. This would change the path of hurricanes. It could bring storms to places that were once calm. It could make dry regions more dry and wet regions more wet. The Arctic is more than a frozen ocean. It is a place that controls the rhythm of the Earth. It is where water meets cold and becomes part of a global system. It shares heat and cold with distant lands. It sends signals to the atmosphere. It shapes the future of the climate. Scientists know that studying the Arctic is not just about exploring a remote region. It is about understanding the whole planet. The world above the ice and the world below are part of the same story. The Arctic's depths hold answers about the past and warnings for the future. The ocean currents move slowly and steadily. The atmosphere shifts and forms new patterns. And beneath the frozen surface, the Arctic continues to operate as one of Earth's most powerful engines. It reminds us that even the quietest places shape the world we live in. To explore the Arctic today requires patience, caution, and an understanding of the cold. But to explore it tomorrow demands something more. It demands tools shaped not just for harsh weather, but for mystery. Tools designed to see through ice and travel through a world where light cannot reach, where the ocean bends sound, where the currents shift without warning, where pressure and cold turn metal brittle. So scientists and engineers continue to imagine new ways to reach into the depths. One of the most remarkable breakthroughs has come from ice-penetrating radar. These instruments send gentle waves into the frozen surface. The radar travels down through the layers of ice and reflects back to the device. Every layer of frozen water changes the signal slightly. The reflection reveals the thickness and texture of the ice. It shows where cracks form and where openings appear. For the first time, researchers can see beneath the surface without breaking it. They can map the shape of the ice roof from above. They can follow its movements and its hidden patterns. This technology helps scientists find safe routes for submarines. It helps them understand how the ice forms and melts. It allows them to track the ice as it drifts across the Arctic. Some versions of this radar can even reach the ocean below. They show where fresh and salt water meet. They reveal pockets of trapped currents and hidden layers. These images are like windows into the story of the Arctic. They let us watch the ice move even when the surface looks still. But radar is only part of the future of exploration. Beneath the ice, a new generation of machines is beginning to travel through places no human has ever seen. These machines are autonomous under ice drones. They do not rely on constant control from the surface. They are designed to think and move on their own. An autonomous drone can glide silently through the dark. It uses sonar and sensors to navigate. It maps the seafloor and the underside of the ice. It listens for changes in sound and pressure. It adjusts its path as the environment shifts. The drone does not need a guide. It follows its programming and adapts to conditions it was never shown. Some of these drones are shaped like torpedoes. Others resemble small submarines. Some are tiny and light, able to squeeze through narrow spaces. Others are large, capable of traveling great distances beneath the ice. Each design serves a different purpose. Together, they allow researchers to gather information that once seemed impossible to obtain. These drones carry cameras built for darkness. They shine gentle lights that reveal shapes in the water. They capture images of creatures and caves. They hover above vents and sediment layers. They drift along currents and record the flow of the ocean. Their sensors detect temperature and salt. They measure sound and magnetic fields. Every second of movement collects data that expands our understanding of the Arctic. Because these machines can travel without being tethered to a ship, they can reach places that once were unreachable. They glide beneath thick ice sheets. They move through deep and narrow channels. They remain below the surface for long stretches of time. They witness changes in the environment that no satellite or human eye can see. The future of exploration goes even deeper. Researchers imagine fleets of drones traveling together through the Arctic. They communicate with one another and share information. They create maps that are more detailed than ever before. They follow currents and trace the shape of the seafloor. They build a picture of a world that was hidden for thousands of years. Seafloor mapping is one of the most important goals of these tools. The Arctic seafloor holds ancient water and geological secrets. It contains ridges and valleys that guide the ocean currents. It stores chemical records and minerals. Mapping this landscape helps scientists understand how the ocean formed. It reveals how tectonic forces shape the world over time. Traditional mapping requires ships to travel across the surface of the ocean, but in the Arctic, the surface is often blocked by ice. The drones and radar change this. They allow mapping to continue even when the ice does not move. They create images of the deep ocean in real time. They show the world beneath the frozen roof with clarity. These tools are not just technological achievements, they are keys to understanding a world that remains mysterious. They help us learn how the Arctic responds to change. They prepare us for the future of exploration. The ice will not become easier to cross. The ocean will not become less deep, but the tools of tomorrow make the unknown less distant. The Arctic invites us to listen, to look, and to learn. The tools we build today will open the paths of tomorrow. They will guide us through the darkness and reveal the world beneath the ice. Each new invention is a quiet promise, a promise that the story of the Arctic is far from over. The deeper we drift into the Arctic, the more we discover how little we truly understand. It is not simply a frozen landscape at the top of the world. It is a system of currents, silence, pressure, and memory. It guards ancient water and living light. It holds the remains of past explorers and the voices of unknown creatures. It changes without warning, and yet it has remained untouched in many ways for thousands of years. Even now, after so many expeditions and studies, the Arctic continues to resist being known. It keeps its secrets beneath layers of ice and darkness. It shifts, drifts, melts, and reforms. It isolates the deep ocean from the rest of the world. It allows life to flourish where sunlight cannot enter. It turns steel into weakness. It stops machines with cold and silence. Every discovery only leads to another question. The Arctic remains one of Earth's last great frontiers. It is a place where the ancient rhythms of the planet are still powerful. It is where the deep oceans begin and where global currents are shaped. It is where the wind and the sea meet to create storms that circle the world. It connects the continents and the climates. It binds the past and the future together. From the oldest water held in hidden basins to the sounds echoing beneath the ice, the Arctic teaches us that the world is larger than what we see on maps. The ocean floor is carved by forces older than humanity. The seafloor preserves the history of continents and the traces of ancient climates. Sediments hold chemical stories that stretch back through time. Microbes and fish live in darkness without the help of the sun. Bioluminescent organisms turn the deep into a quiet constellation. We learn not just about ice or cold, but about life. We see how organisms survive in places that appear impossible. We see how geology shapes oceans and how oceans shape the planet. We see how a single region can influence the climate of the entire world. The Arctic becomes a reminder that every environment is connected. What happens in one place echoes in another, even far away. Exploring this place is a challenge, and always will be. The tools of tomorrow will travel beneath the ice. Radar and drones will see what human eyes cannot. They will map hidden currents and valleys. They will listen to ancient sounds and measure the changes in temperature and pressure. They will collect stories from the ocean floor and bring them back to the surface. What we learn from these discoveries may reshape our understanding of climate science. It may reveal how the oceans control the weather and how the Earth responds to change. It may show us how life begins and adapts. It may help us understand how the planet will transform in the future. The Arctic is not just cold and distant, it is a guide and a teacher. There is still so much that we do not know. The silence beneath the ice carries the past. The currents carry the story of the future. The Arctic is a world that continues to move and breathe in its own time. It invites us to look closer, but it never reveals everything. It holds mysteries that remain untouched. So we return to the surface for now, with the echoes of the deep still drifting across our thoughts. We carry the stories of lost machines, ancient waters, and hidden life. We carry the knowledge that the Arctic is more than a frozen ocean. It is a living archive of Earth's history. Thank you for joining this quiet journey into the cold and the unseen. If you enjoyed exploring these hidden wonders and drifting into the deep with us, consider liking this video and subscribing to the channel. There are more places to visit and more stories waiting beneath the surface of our world. For now, rest gently in the thought that the Arctic continues to watch over its secrets. The ice hides more than mysteries. It hides the long memory of the planet, and its story is far from over.